Hello there, and welcome to Science for Sleep, where curiosity gets cozy and science takes the scenic route to rest. Tonight's quiet journey drifts far beyond our everyday sense of distance, past the familiar glow of stars and into a corner of the universe where something extraordinary once happened. Not loud in the way we experience sound, not bright in the way our eyes can see, but powerful in a way that quietly reshaped our understanding of what a single object can do when pushed to its limits. Somewhere out there, about 50,000 light-years away, a star did something so intense that even across that enormous distance, instruments around Earth noticed. Not because we were looking directly at it at the time, but because the signal was simply too strong to ignore. It arrived like a sudden ripple through space itself, brief, overwhelming, and strangely precise. Now, before we get carried away with that idea, let's slow things down a little. This isn't a story about destruction in the dramatic cinematic sense. It's not about danger looming overhead or something to worry about. Instead, it's about scale. About what happens when nature stretches the rules we're used to just a bit further than we expect. And about how, even from a safe and comfortable distance, we can quietly observe something that, for a brief moment, became the most powerful explosion ever detected. But before we continue, let me ask you something simple. Where are you listening from right now? And what time is it where you are? It's a small question, but it always feels fitting, especially when we're about to talk about something that happened so far away that in a sense it didn't happen now at all. The signal we're going to explore left its source long before any of us pressed play on this video. It travelled patiently through space, crossing distances that are difficult to picture, until eventually it brushed past Earth and quietly announced its arrival to a handful of machines orbiting our planet. If you find this kind of slow, curious exploration calming, or simply a nice way to wind down, you might consider giving the video a like or subscribing to the channel. It helps this quiet little space reach others who might enjoy a gentle journey like this one. Now, let's settle in and begin. Because the story we're stepping into doesn't start with the explosion itself. It starts with a feeling, a sense that every now and then, the universe does something so unexpectedly intense that it reminds us just how wide the range of possibility really is. You might imagine space as calm and still, a vast emptiness where not much happens unless we go looking for it. And for the most part, that's not entirely wrong. Much of the universe unfolds slowly. Stars burn for millions or billions of years. Galaxies drift gradually through space. Even collisions on a cosmic scale take place over time spans so long that they feel almost frozen. But every so often, something breaks that calm. Not with noise, because space doesn't carry sound the way air does. Not with visible light, at least not always. But with energy. Sudden, concentrated, and surprisingly brief. The event we're talking about tonight lasted less than a second in its most intense phase. Less than a second. And yet, during that fraction of time, it released more energy than our sun produces in hundreds of thousands of years. It's one of those comparisons that feels almost too large to hold on to. So instead of trying to grasp it all at once, it helps to take a step back and approach it slowly, piece by piece. Imagine, for a moment, the sun. Not as a distant glowing disk in the sky, but as a steady engine. Every second it converts an enormous amount of mass into energy, radiating light and heat in all directions. This process has been going on for billions of years, quietly supporting life here on Earth. Now imagine taking hundreds of thousands of years of that steady output and compressing it into a single instant. That's the kind of scale we're dealing with. And yet, despite that intensity, despite that sudden burst of energy, it happened so far away that by the time its effects reached us, it was more like a whisper than a shout. Or perhaps more accurately, a flicker. A very precise, measurable flicker. It was December 27th, 2004. At first, nothing seemed unusual to anyone going about their day. People were waking up, making tea or coffee, checking their phones, stepping outside into whatever weather greeted them. The world, as far as anyone could tell, was entirely normal. But above the Earth, orbiting quietly, several satellites were doing something a little different. They were watching, or more specifically, they were listening in their own way to a part of the universe we can't perceive directly. Instruments designed to detect gamma rays, the most energetic form of light, were continuously scanning the sky. Not with eyes, but with sensors tuned to catch bursts of energy that might otherwise go unnoticed. And then, suddenly, they all registered something at once. A sharp spike, not subtle, not gradual, immediate. For a brief moment, detectors that were built to observe distant cosmic events were overwhelmed. Some even saturated, meaning the signal was so strong that it exceeded what they were designed to handle. That alone was unusual. Gamma-ray bursts do happen. They're not entirely rare in cosmic terms, but this one was different. It was closer than most, and it was far more intense than anything previously recorded from that kind of source. At first, scientists weren't entirely sure what they were looking at. When multiple instruments across different satellites all react at the same time, it's a clue that something significant has occurred. But understanding exactly what that something is can take time, so they did what scientists tend to do in moments like this. They gathered data, they compared signals, they checked for patterns, and slowly a picture began to form. The signal had come from a known object. Not something entirely new, but something already catalogued and studied, though not fully understood. Its name was SGR 1806-20. A rather technical designation, but behind it was something far more unusual than the name suggests. At this point, you might be wondering what exactly produced such an intense burst of energy. Was it a supernova, a black hole, something colliding with something else? Interestingly, no. It wasn't a star exploding in the traditional sense. It wasn't matter falling into a black hole either. It was something smaller, much smaller than a typical star, and yet, in terms of intensity, it briefly outshone entire regions of the galaxy. To understand how that's possible, we need to gently shift our perspective. Instead of thinking in terms of size alone, we start thinking in terms of density, of pressure, of conditions that push matter into states we don't encounter anywhere in everyday life. Because SGR 1806-20 isn't just any star. It's what we call a magnetar. Now, that word might sound a bit unfamiliar, and that's perfectly fine. We're not going to rush through it. We'll take our time with it the same way we've been doing so far. For now, it's enough to say that a magnetar is a type of neutron star. And a neutron star, in turn, is what's left behind after a massive star has reached the end of its life and collapsed under its own gravity. But this isn't collapse in the way we might imagine something falling inward and simply disappearing. It's compression. Extreme compression. So extreme that the core of a star, something originally larger than the sun, gets squeezed down into an object only about 20 kilometers across, roughly the size of a city. And yet, it contains more mass than the sun itself. It's difficult to picture, so it helps to simplify it. If you could take a small amount of that material, even something the size of a teaspoon, it would weigh billions of tons on Earth. Not because it's large, but because it's incredibly dense. Everything is packed together so tightly that atoms themselves are crushed. Electrons and protons combine into neutrons, forming a kind of matter that doesn't behave like anything we encounter in our daily lives. Now, most neutron stars are already extreme by these standards, but magnetars take things even further. They possess magnetic fields so strong that they don't just influence nearby particles, they can affect the very structure of matter itself. If you were somehow able to get close enough, which we definitely wouldn't recommend, those magnetic forces could distort atoms, stretch them, and change how they behave. Even at a distance, their influence is significant, and every now and then, under certain conditions, that stored energy doesn't remain contained. It releases, not gradually, but suddenly, like tension snapping. Which brings us back to that moment in 2004 when SGR 1806-20 did exactly that. But before we fully step into that event itself, it might be worth pausing here for just a moment, because understanding what happened requires us to get comfortable with the idea that not all explosions are created equal. Some are driven by collisions, others by collapse, and some, like this one, are driven by something less familiar: magnetism. Not the kind that holds a note to your fridge, but something far more powerful. Something about that moment still feels a little unreal when you slow it down and look at it closely, because what the satellites detected wasn't just a strong signal, or even an unusually bright one. It was, for a brief instant, something that outshone almost everything else in its part of the sky. Not in visible light, not in a way anyone could glance up and notice, but in gamma rays, the most energetic form of light we know. And it didn't build up slowly, it arrived all at once. If you imagine a quiet room where nothing much is happening, and then, without warning, every light switches on at full brightness for a fraction of a second, you get a sense of how sudden it was. Except here, instead of light bulbs, we're talking about detectors designed to measure some of the most extreme phenomena in the universe. On December 27th, 2004, multiple satellites orbiting Earth recorded a spike so intense that some of them temporarily lost their ability to measure it accurately. The signal saturated their instruments, meaning the incoming energy exceeded what they were calibrated to handle. It's a bit like trying to measure a wave with a ruler, only to find the wave is taller than the ruler itself. That alone tells you something unusual had happened. Now, gamma-ray bursts are not entirely uncommon in cosmic terms. They occur when massive stars collapse or when neutron stars merge. These events release enormous amounts of energy, often visible across vast distances. Scientists have been detecting them for decades. But this wasn't quite the same thing. This was different in two important ways. First, it was much closer than most gamma-ray bursts we observe. Not close in the everyday sense, of course, still tens of thousands of light years away. But compared to events occurring in distant galaxies billions of light years away, this one was practically in our neighbourhood. Second, and more importantly, it was incredibly intense. To understand just how intense, it helps to slow things down and imagine what those detectors actually saw. For a fraction of a second, the incoming gamma rays surged to a level that, if translated into visible brightness, would have outshone the full moon, despite originating from an object on the other side of our galaxy. That comparison might sound a bit abstract, so let's ground it. The moon, when full, is one of the brightest objects in our night sky. It reflects sunlight toward us, lighting up landscapes, casting shadows, and quietly dominating the darkness. And it's relatively close, only about 384,000 kilometers away. Now picture something tens of thousands of light years away, shining with such intensity in its own form of light that it could rival that brightness if our eyes were sensitive to gamma rays. That's what happened. And it didn't last long. The most intense part of the flare peaked in about 1/10 of a second, just a blink. But in that blink, the energy released was staggering. Scientists estimate that the total energy emitted during the flare was equivalent to what our sun would produce over roughly 150,000 years. Again, it helps to pause there. The sun, quietly shining above us every day, is constantly producing energy. It warms the earth, drives weather systems, fuels life. And it does this steadily, second after second, year after year. Now compress 150,000 years of that output into a fraction of a second. That's not just a difference in scale, it's a difference in how we think about energy entirely. And yet, despite that immense release, the Earth was not harmed. That might seem surprising at first. After all, if something that powerful can be detected so clearly across the galaxy, shouldn't it have had some noticeable effect on our planet? The answer is both reassuring and fascinating. Distance matters. A lot. Even though the flare was extraordinarily powerful, it spread out as it travelled through space. By the time it reached Earth, it was diluted. its energy distributed across a vast sphere expanding in all directions. So instead of arriving as destructive force, it reached us as a measurable signal. Still, measurable doesn't mean insignificant. The flare was strong enough to have subtle effects on Earth's upper atmosphere. In fact, it briefly altered the ionosphere, a layer of Earth's atmosphere filled with charged particles. This layer plays a role in how radio waves travel, and during the event, scientists noticed slight disturbances, as if the atmosphere itself had momentarily responded to something it couldn't see. It's a quiet kind of interaction. No flashes in the sky, no sounds, no visible changes to the world around us. Just a subtle shift, detectable only through careful measurement, which makes it all the more interesting, because it reminds us that the universe is constantly interacting with us in ways we don't always notice. Signals arrive, pass through, leave traces, and continue on. Most of the time, they're too faint to matter, but every now and then, something stands out. Now, going back to the satellites, it wasn't just one instrument that detected the flare. Multiple spacecraft, each with different orientations and sensitivities, recorded the event almost simultaneously. This allowed scientists to triangulate its origin. By comparing the timing of the signal's arrival at different locations, they could determine where in the sky it had come from, and when they traced it back, it pointed to a known source, SGR 1806-20. At that point, researchers realized they were witnessing something called a giant flare. Not a typical gamma-ray burst, but a specific kind of event associated with magnetars, and giant flares are rare. Very rare. Only a handful have ever been observed, and this one was by far the most powerful. It's interesting to think about how such a brief event can carry so much information. In less than a second, it told scientists about the strength of magnetic fields, the structure of neutron stars, and the kinds of stresses that can build up in such extreme environments. It also raised new questions. Why did it happen at that moment? What conditions led to such a sudden release? And perhaps most intriguingly, could it happen again? But before we explore those questions, it helps to understand what the flare actually looked like in more detail. Because even though the peak lasted only a fraction of a second, the event as a whole unfolded in stages. The initial spike was followed by a tail, a fading signal that lasted several minutes. During this time, the brightness gradually decreased, but it didn't do so smoothly. It pulsed, regularly, like a heartbeat. This pulsing matched the rotation of the magnetar itself, which means that as the object spun, beams of radiation swept past Earth at regular intervals, much like a lighthouse beam rotating across the ocean. That detail alone tells us something remarkable. Even in the aftermath of such a powerful release, the structure of the magnetar remained intact enough to continue rotating and emitting radiation in a predictable way. It didn't destroy itself. It simply released a portion of its stored energy and carried on. There's something oddly calm about that, an object capable of producing one of the most powerful explosions ever detected, and yet after the event, it continues to exist, to rotate, to quietly emit signals into space. Not dramatically different, not fundamentally changed in a visible sense, just slightly altered. It's a reminder that, in the universe, even the most intense events can be part of an ongoing process rather than a final endpoint. And if you think about it, that idea shows up in other places too. Storms pass, but the atmosphere remains. Waves crash, but the ocean continues. Energy builds, releases, and then settles again. The same pattern, just on a much larger scale. Now, if we shift our focus slightly, another interesting aspect of this flare is how it compares to other cosmic events. Supernovae, for example, can release vast amounts of energy over longer periods. Gamma-ray bursts from collapsing stars can outshine entire galaxies for seconds or minutes, but those events often occur much farther away. What made this one special was its combination of intensity and proximity. It was close enough to be studied in detail, and powerful enough to stand out even among the most energetic phenomena we've observed. That combination is rare, and it gives scientists a valuable opportunity, because when something like this happens relatively nearby, the data we collect is clearer, richer, and more informative. It allows us to test theories, refine models, and better understand the underlying physics. In a way, it's like hearing a distant sound more clearly because it's closer than usual. You can pick out details you might otherwise miss. And in this case, those details pointed towards something both fascinating and slightly counterintuitive, that such an enormous release of energy could come from something so compact. Not a massive star spanning millions of kilometers, but an object only about 20 kilometers across. A city-sized remnant, dense, quiet, and usually stable. Until occasionally it isn't. Which brings us gently back to the question we paused on earlier. What exactly causes a magnetar to release energy in such a sudden and dramatic way? Because understanding that requires us to look not just at what a magnetar is, but how it behaves over time, how energy builds within it, how stress accumulates, and what happens when that stress finally becomes too much to contain. For most people, that day passed without anything unusual at all. Morning routines unfolded as they always do. Someone poured coffee, someone else checked the weather, a few alarms were snoozed and forgotten. Cars moved through streets, conversations started and ended, and the quiet rhythm of daily life continued without interruption. If you had stepped outside and looked up, the sky would have appeared exactly as expected. No flashes, no sudden brightness, no sign that anything remarkable had just happened. And yet, something had. Not in a way you could feel through your feet or hear in the air, but in a way that quietly brushed past the invisible system surrounding our planet. A signal, travelling for tens of thousands of years, arrived and interacted with Earth in a subtle but measurable way. It's a curious thought, isn't it? That something so distant, so far removed from our everyday experience, could still leave a trace here, even if only for a moment. Because while the explosion itself occurred about 50,000 light-years away, the energy it released didn't stay there. It spread outward in all directions, expanding through space like a ripple across a very, very large pond. And eventually, after crossing distances that are difficult to imagine, a small fraction of that energy reached Earth. Now, before we go any further, it helps to gently set expectations. This wasn't a shock in the way we usually think of one. There was no jolt, no sudden movement of the ground, no visible disturbance in the sky. If you were standing outside at the exact moment the signal passed through, you wouldn't have noticed anything at all. But instruments did, and those instruments tell us a story that's both subtle and fascinating. High above the Earth, satellites are constantly monitoring different parts of the electromagnetic spectrum. Some are watching visible light, others are tuned to radio waves, X-rays, or gamma rays. Each one is designed to pick up signals that our senses can't detect. When the flare from SGR 1806-20 arrived, it interacted first with the outermost layers of Earth's environment, specifically the ionosphere. The ionosphere is a region of the upper atmosphere filled with charged particles. It's shaped by sunlight, cosmic radiation, and the Earth's magnetic field. It plays a quiet but important role in things like radio communication, helping signals travel long distances by reflecting them back toward the surface. Most of the time, the ionosphere changes gradually, influenced by the day-night cycle and solar activity. But occasionally it responds to something more sudden, and on that day in 2004 it did. The incoming burst of gamma rays briefly increased the level of ionization in that upper layer. In simple terms, it added energy, knocking electrons free from atoms and slightly altering the balance of charged particles. This change was small, very small, but measurable. Researchers studying the ionosphere noticed a brief disturbance, a kind of ripple in its usual behavior. It wasn't dramatic enough to disrupt everyday life, but it was enough to confirm that the flare had interacted with Earth in a direct, physical way. It's almost like a whisper passing through a room. You might not hear it, but a sensitive microphone could pick it up. And in this case, our microphones were both satellites and ground-based instruments designed to monitor the atmosphere. Now, if we slow down and think about what that means, it becomes quite interesting. Because this wasn't just a distant event observed from afar, it was an event that reached us, interacted with our planet, and left behind a trace, however faint. It's a reminder that space isn't entirely separate from us. There's a constant exchange happening. Energy moves through it, signals pass through it, and every now and then something arrives that stands out just enough to be noticed. Another subtle effect of the flare was observed in communication systems. Very low-frequency radio waves, which travel through the ionosphere, showed slight disturbances during the event. These changes were brief and didn't cause noticeable problems for most systems, but they were consistent with the idea that the atmosphere had been temporarily altered. Again, nothing dramatic, just a small shift. But when you consider the source of that shift, it becomes more remarkable, because it means that a single object located halfway across our galaxy released enough energy in a fraction of a second to measurably affect the upper atmosphere of a planet tens of thousands of light years away. Not in a destructive way, not in a dangerous way, but in a way that we can detect and study. And that brings us to another interesting point. Timing. The signal didn't arrive in stages separated by years or centuries. It arrived almost all at once, at least from our perspective. That's because the flare itself was so brief. The most intense part lasted only a fraction of a second, followed by a fading tail that stretched out over several minutes. But the leading edge, that initial spike, hit Earth as a sharp, sudden increase in gamma radiation. Satellites detected it nearly simultaneously, confirming that it was a real, external event rather than something local or instrumental. And because these satellites are spread out in different orbits, their combined data allowed scientists to reconstruct the direction and origin of the signal with surprising accuracy. It's a bit like hearing a sound with both ears and using the slight difference in timing to figure out where it came from. Except here, the ears are orbiting thousands of kilometers apart, and the sound is a burst of gamma rays travelling at the speed of a light. Now, there's something quietly comforting about how all of this unfolded, because despite the immense energy involved, the Earth remained entirely safe. The atmosphere absorbed the incoming radiation, as it does with many forms of high-energy light. The surface of the planet was shielded, and life continued uninterrupted. It's a reminder of just how effective our atmosphere is as a protective layer. It filters out harmful radiation, moderates temperature, and creates conditions that allow life to exist in relative stability. Without it, events like this might feel very different. But with it, even something as powerful as this flare becomes more of a scientific curiosity than a cause for concern. Still, it does raise an interesting question. What if it had been closer? We won't dwell on that too much because there's no need to turn this into something unsettling. But it's worth acknowledging that distance plays a crucial role in how we experience cosmic events. The farther away something is, the more its energy spreads out before reaching us, and in this case that distance was more than enough to reduce a truly enormous explosion to something subtle and manageable. Now, going back to the idea of Earth feeling the event, it's important to keep that word in context. This wasn't a feeling in the human sense. No one sensed it directly, no instinct picked it up. Instead, it was the kind of feeling that comes from measurement, from instruments designed to notice changes that are far too small or too fast for us to perceive. And that's part of what makes modern science so fascinating. It extends our senses. It allows us to detect things that would otherwise pass by unnoticed. And in doing so, it connects us to events happening across the universe in ways that feel both distant and immediate at the same time. Because even though the flare occurred 50,000 years ago in terms of when the light left its source, it arrived here in a single, shared moment. A moment when satellites recorded the same spike. when data was collected, when something that had been travelling through space for tens of thousands of years finally reached its destination. There's something quietly poetic about that, even if we're keeping things grounded and simple. A signal leaving its source long before recorded human history, crossing the galaxy and arriving just in time to be detected by instruments we built only recently. It's a convergence of timing that feels almost unlikely. And yet, it happened. Now, as we move forward, it helps to keep that sense of scale in mind. Not just the energy involved, but the distance, the timing, and the subtle way in which it interacted with our planet. By the time the initial burst had passed and the instruments had settled back into their normal ranges, there was already a quiet shift happening among the scientists studying the data, because detecting something is only the beginning. The next step, often slower and a bit more patient, is figuring out exactly where it came from. At first glance, that might sound straightforward. A signal arrives, you trace it back, and there it is. But in practice, it's a little more like trying to locate a distant flash of lightning when you didn't see the clouds that produced it. You have clues, you have timing, and you have direction, but you don't have a simple line pointing neatly back to the source. So instead, researchers rely on something more subtle. They compare. They look at how the signal arrived at different detectors, at slightly different times, and from slightly different angles. Each satellite, orbiting Earth in its own path, recorded the flare with its own tiny variation in timing, and those variations, when carefully measured, form a kind of map. Not a visual map you can hold in your hands, but a mathematical one. By aligning those signals, scientists can narrow down a region of the sky where the burst must have originated. It's a bit like hearing a distant sound with both ears and instinctively knowing which direction to turn your head. Except here the ears are spread across space, and the sound is a burst of gamma rays that travelled for 50,000 years. And when they did that, when they compared the data and traced the signal back across the sky, everything pointed to a familiar place, a source that had been observed before, SGR 1806-20. Now, the name itself doesn't tell you much at first glance. It sounds technical, almost like a catalogue number, and in many ways that's exactly what it is. SGR stands for Soft Gamma Repeater. The numbers that follow indicate its position in the sky. It's not a poetic name, but it reflects something important about how this object was first discovered. Because long before the 2004 event, astronomers had already been watching it. Not constantly, not every second, but enough to notice a pattern. Every so often it would emit short bursts of gamma rays. Not enormous galaxy-spanning flares, but smaller, more frequent pulses. These bursts were irregular, unpredictable, and usually brief. They didn't last long, and they didn't release nearly as much energy as the giant flare we've been discussing. But they were enough to mark the object as something unusual, something worth keeping an eye on. And over time, as more of these bursts were recorded, scientists began to group similar objects together. They noticed that these soft gamma repeaters shared certain characteristics. They were compact, highly energetic, and often associated with remnants of massive stars. Eventually, a clearer picture began to form. These objects weren't just random sources of radiation. They were a specific kind of neutron star, magnetars. But we'll take our time with that idea in just a moment. For now, it's enough to know that SGR 1806-20 was already on the map, quietly known to astronomers as a source of occasional gamma ray activity. And then, in December 2004, it did something very different. Something far more intense than anything it had done before. When scientists traced the giant flare back to its origin, the fact that it came from a known object was both helpful and surprising. Helpful because it meant they already had some information to work with. Surprising because it showed that an object capable of relatively modest bursts could, under the right conditions, produce something vastly more powerful. It's a bit like knowing a calm lake that occasionally ripples in the wind, and then one day witnessing a sudden enormous wave rise from its surface. You know the lake, you've seen it before, but you didn't expect that. Now, locating SGR 1806-2O in the sky isn't something you can do by simply looking up. It's far too distant, and it doesn't emit visible light in a way that stands out to the naked eye. Instead, its presence is revealed through the signals it emits: gamma rays, X-rays, forms of light that require specialized instruments to detect. In fact, if you were to point a regular telescope at its location, you might not see anything remarkable at all. It's hidden behind clouds of gas and dust in our galaxy, in a region that's not particularly easy to observe in visible wavelengths. But in higher energy light, it becomes much more apparent, and that's how it was studied. Over the years, astronomers used X-ray observatories and gamma-ray detectors to monitor its behavior. They tracked its bursts, measured their intensity, and tried to understand what kind of object could produce them. They also looked at its environment. SGR 1806-2O is located in a dense region of the Milky Way, near a cluster of massive stars. This region is active, full of stellar formation and remnants of past explosions, is not a quiet corner of the galaxy, and that context matters, because objects like magnetars are often born in such environments. They begin as massive stars many times larger than our Sun, living relatively short but intense lives. When those stars reach the end of their fuel supply, they collapse, triggering a supernova explosion that leaves behind a compact core. In some cases, that core becomes a neutron star, and in even rarer cases, it becomes a magnetar. SGR 1806-2O is one of those rare cases. But before we fully explore what that means, there's something else worth noticing about how we found it. Because in a sense, we didn't find it in 2004, we rediscovered it. The object was already known, already catalogued, already studied, but the giant flare revealed something new about it, something that hadn't been fully appreciated before. It showed that this wasn't just a source of occasional gamma-ray bursts, it was capable of producing one of the most powerful explosions ever detected. And that changes how you think about it. It shifts it from being an interesting object to being a key example of a much more extreme phenomenon. Now, when scientists study objects like SGR 1806-2, they don't just look at individual events, they look at patterns over time. They ask questions like, how often does it produce smaller bursts? How does its rotation change? What does its spectrum of radiation look like? These details help build a more complete picture. For example, SGR 1806-20 rotates relatively slowly compared to some neutron stars, completing a rotation roughly every 7.5 seconds. That might sound fast, but in the world of neutron stars, where some spin hundreds of times per second, it's actually quite measured. That slower rotation, combined with its emission patterns, is one of the clues that identifies it as a magnetar rather than another type of neutron star. Another clue comes from how its bursts behave. The smaller, more frequent bursts are thought to be caused by minor adjustments in its structure, small releases of energy as the star's magnetic field shifts and settles. But the giant flare in 2004 was something else entirely. It was the result of a much larger release of stored energy. And understanding how that energy builds up is the key to understanding the object itself. Now, if we step back for a moment, there's something quietly satisfying about how this discovery unfolded. It wasn't a single observation that revealed everything. It was a combination of years of data, multiple instruments, and careful analysis, a gradual process, and then suddenly, a single event that tied it all together. It's a pattern that shows up often in science. Long periods of quiet observation, followed by a moment of clarity. And in this case, that clarity came in the form of a flare so intense that it briefly overwhelmed the tools designed to measure it, which, in a way, is the universe's way of saying, you might want to take a closer look at this. So now that we know where the signal came from, and that it originated from a known object called SGR 1806-20, the next step is to understand what kind of object it really is, because the name soft gamma repeater only tells part of the story. It describes what it does, not what it is. And what it is turns out to be something far more unusual, something that pushes matter, energy, and magnetism into a range that feels almost unfamiliar even when explained slowly. Before we go any further into the flare itself, it helps to pause for a moment and look more closely at the kind of object we're dealing with. Because the name SGR 1806-20, while useful, doesn't really capture what makes it special. To understand that, we need to gently unpack a single word: magnetar. Now, at first glance, it sounds like something out of science fiction. A dramatic name, maybe even a bit exaggerated. But in this case, the name is actually quite literal. A magnetar is, quite simply, a star defined by its magnetism. Not in the casual sense like a fridge magnet holding up a note, but in a way that stretches the concept of magnetism far beyond anything we experience in everyday life. And the story of a magnetar doesn't begin as something exotic. It begins as a star, a very massive star. Imagine something several times larger than our sun, burning brightly, fusing elements in its core, and living a life that, while intense, is still governed by the same basic rules as any other star. It shines, it produces energy, and it balances the inward pull of gravity with the outward pressure from nuclear fusion. For millions of years that balance holds, but eventually the fuel runs out, and when it does, gravity takes over. The star can no longer support itself, and its core collapses inward in a fraction of a second. The outer layers are blown away in a supernova, one of the most energetic events in the universe. What's left behind is the core, and that core becomes something entirely different, a neutron star. Now, we touched on this briefly earlier, but it's worth slowing down here because neutron stars are already among the most extreme objects in the universe. Take the mass of a star, something larger than the sun, and compress it into a sphere about 20 kilometers across, roughly the size of a city. The result is an object so dense that a single teaspoon of its material would weigh billions of tons, not because it's large, but because everything inside it is packed together with incredible force. Atoms don't survive this process in the way we're used to. The pressure is so intense that electrons and protons are pushed together to form neutrons, creating a kind of matter that behaves very differently from anything we encounter on Earth. So even before we add anything else to the picture, a neutron star is already an extreme place. But a magnetar goes further, much further. What sets a magnetar apart from other neutron stars is its magnetic field. And this is where things become a bit difficult to visualize, so we'll take it slowly. The Earth has a magnetic field. It's what allows compasses to point north, and it helps shield us from charged particles coming from the sun. It's strong enough to guide navigation and shape the behavior of the upper atmosphere, but it's relatively gentle. A typical fridge magnet is stronger than Earth's magnetic field. Now, if we scale up, a normal neutron star has a magnetic field that is already trillions of times stronger than Earth's. That alone is enough to affect nearby matter in dramatic ways. But a magnetar's magnetic field is about 1,000 times stronger than that of a typical neutron star. Which means it's not just strong, it's extraordinarily strong. To give that some perspective, if a magnetar were placed halfway between the Earth and the Moon, its magnetic field would be strong enough to erase every credit card on our planet. Not by touching them, but simply by being there. And that's from a distance of hundreds of thousands of kilometers. If you were somehow much closer, the effects would be even more unusual. The magnetic field could begin to distort atoms themselves. Normally, atoms are roughly spherical, with electrons moving in cloud-like regions around a nucleus. But in a magnetic field this strong, those structures can stretch, becoming elongated, almost like thin strands. Matter itself starts to behave differently. Even light can be affected. In extremely strong magnetic fields, the vacuum of space can act in unusual ways, altering how light propagates through it. It's a subtle effect, but it's one of those places where the rules we're familiar with begin to shift. Now, all of this might make a magnetar sound unstable or chaotic, but most of the time it isn't. Most of the time it's quiet. It rotates. It emits radiation. It exists. And if you were observing it from a safe distance, it might not seem particularly dramatic. But beneath that calm surface, there's something important happening. Energy is being stored, not in the form of heat or motion, but in the magnetic field itself. You can think of it a bit like tension. If you take a piece of metal and bend it slightly, it stores a small amount of energy. Bend it further, and the stress increases. At some point, if the stress becomes too great, the material might crack or snap, releasing that stored energy suddenly. A magnetar behaves in a somewhat similar way, though on a much larger and more complex scale. Its magnetic field is so strong that it places enormous stress on the star's crust. Yes, crust. Even though a neutron star is incredibly dense, it still has a kind of outer layer, a solid surface, often described as a crust. It's not like the crust of the Earth, but it does have structure, and it can experience strain. Over time, as the magnetic field shifts and evolves, that stress builds, very slowly, very quietly, and most of the time it releases in small ways, tiny adjustments, minor shifts. These are the smaller bursts that objects like SGR 1806-2 were known for before 2004. Short flashes of gamma rays caused by relatively small releases of energy as the star's magnetic field rearranges itself. But occasionally the stress becomes too much, and when that happens the crust can crack. Not gently, not gradually, but suddenly. This is what scientists refer to as a star quake. It's similar in concept to an earthquake, where stress builds up along faults in the Earth's crust until it's released in a sudden movement. But in the case of a magnetar, the forces involved are far greater, and the consequences are much more energetic. When the crust cracks, it triggers a rapid reconfiguration of the magnetic field, and that reconfiguration releases a huge amount of energy that had been stored over time suddenly set free. This is what produces a giant flare, the kind of event we observed from SGR 1806-20. Now, it's worth noting that magnetars are relatively rare. Out of all the stars in the galaxy, only a small fraction end their lives in a way that produces a magnetar. And even among neutron stars, magnetars represent a special category, defined by these extreme magnetic fields and the behaviour that comes with them. So when we observe one, especially one that produces a giant flare, it becomes a valuable opportunity, because it allows us to study physics under conditions that can't be replicated anywhere else. We can't create a magnetar in a laboratory. We can't reproduce those magnetic fields, but we can observe them, we can measure their effects, and we can slowly build an understanding of how they work. Now, if we step back and look at the bigger picture, there's something quietly remarkable about this. An object only about 20 kilometers across, smaller than many cities, capable of storing and releasing energy on a scale that rivals entire stars. It challenges our intuition. We tend to associate size with power, thinking that bigger things must always be more energetic. But magnetars show us that density and structure can matter just as much. It's not just how big something is, it's how it's put together, and how much energy it can hold. So as we move forward, it becomes a bit easier to understand how something like SGR 1806-20 could produce such an intense flare. It's not just a star, it's a star under extreme conditions, with a magnetic field that's constantly shifting, building tension, and occasionally releasing it in dramatic ways. Even though magnetars are already unusual, the story doesn't stop there. Long before anything like a magnetar ever exists, there is just a star living a fairly ordinary life by cosmic standards. Not ordinary in the sense of small or quiet, of course. These stars are massive, bright, and short-lived compared to something like our Sun. They burn through their fuel quickly, fusing heavier and heavier elements in their cores, holding themselves up against gravity through the steady release of energy. For millions of years, that balance remains intact. Gravity pulls inward, fusion pushes outward, and the star continues shining without much concern for what comes next. But eventually something begins to change. The fuel that once sustained the star starts to run low. Fusion slows, pressure drops, and gravity, which has been patiently waiting this entire time, begins to take control. What follows is not a gentle transition. It's a rapid and dramatic collapse, one that unfolds in a matter of seconds. The outer layers of the star are thrown outward in a supernova, a bright and violent explosion that briefly outshines entire galaxies. Meanwhile, the core is left behind, no longer supported by fusion, no longer balanced, and so it falls inward, faster, denser, more compressed with every passing moment. At this stage, the physics becomes a bit unfamiliar, so it helps to take it slowly. As the core collapses, atoms themselves begin to break down under the immense pressure. Electrons are forced into protons, forming neutrons. Space between particles disappears. Matter is no longer structured in the way we recognize. It becomes something else entirely. This is how a neutron star is born. An object with more mass than the Sun, squeezed into a sphere only about 20 kilometers wide. Already that description feels like it shouldn't be possible, and in a way, it almost isn't. Because the only thing preventing this collapse from continuing all the way into a black hole is a subtle quantum effect known as neutron degeneracy pressure. It's not something you can see or feel, but it arises from the fundamental rules that govern particles at very small scales. In simple terms, neutrons resist being packed any closer together, not because they push against each other in a mechanical sense, but because the laws of physics forbid them from occupying the same state. That resistance is enough to halt the collapse, just barely. And so, instead of disappearing entirely, the core stabilizes into something incredibly dense and compact, a neutron star. Now, even at this stage, what we're describing is already extreme. A teaspoon of neutron star material would weigh billions of tons. Gravity at the surface is so strong that anything falling onto it would release enormous amounts of energy. Time itself behaves slightly differently near such an object, passing just a bit more slowly compared to farther away. But for most neutron stars, this is where things settle. They rotate, they emit radiation, and they gradually cool over time. Magnetars, however, don't quite follow that path. Something happens during their formation that sets them apart. To understand that, it helps to think about rotation. When a star collapses, its size decreases dramatically, and when something shrinks while spinning, it spins faster. It's the same principle you see when a figure skater pulls in their arms and begins to rotate more quickly. The collapsing core of a massive star behaves in a similar way. As it compresses, its rotation speeds up. In some cases, it spins incredibly fast, completing a full rotation in just a fraction of a second. At the same time, magnetic fields that were already present in the original star become amplified, dramatically. Because as the star collapses, those magnetic field lines are squeezed closer together, increasing their strength. If the conditions are just right, rapid rotation combined with this amplification process can produce a magnetic field far stronger than what's found in an ordinary neutron star. And this is where a magnetar begins to take shape. But it's not guaranteed. Not every collapsing star produces one. The exact details are still being studied, and scientists are still refining their understanding of what conditions lead to the formation of a magnetar rather than a more typical neutron star. It seems to require a combination of factors: a massive progenitor star, a fast initial rotation, and the right internal dynamics during collapse. When those factors align, the result is something unusual: a neutron star with a magnetic field so strong that it changes how the star behaves from the very beginning. At first, this newly formed magnetar is incredibly active. It spins rapidly, emits intense radiation, and gradually sheds energy. Over time, its rotation slows down, and its behaviour becomes less dramatic, at least on the surface. But internally, something important remains. The magnetic field. It doesn't simply fade away, it evolves, shifts, builds tension, and that tension is what sets magnetars apart from other neutron stars. Now, there's something slightly counterintuitive about calling this a star that shouldn't exist, because technically it does exist. We've observed them, we've measured their properties, we've detected their emissions, but the phrase reflects something deeper. It reflects how far these objects push the limits of what we expect from matter and energy. Take the magnetic field, for example. It's so strong that it challenges our usual understanding of how forces operate. In most situations, magnetism is something we can describe fairly simply. It influences charged particles, it creates fields, it interacts with materials. But at the scale of a magnetar, magnetism becomes dominant. It can influence the structure of the star itself. It can distort matter. It can store enormous amounts of energy over long periods of time. And that combination of strength and stability is what makes magnetars feel almost improbable, as if they're sitting right at the edge of what physics allows, not breaking the rules, but certainly stretching them. Another way to think about it is in terms of balance. Most stars are defined by a balance between gravity and pressure. Neutron stars are defined by a balance between gravity and quantum effects. Magnetars introduce something else into that balance: magnetic energy. And not just as a small contribution, but as a major player. In fact, the energy stored in a magnetar's magnetic field can be comparable to the energy released in some of the most powerful events we observe, which means that at any given moment a magnetar is holding onto an enormous reservoir of potential energy, quietly, without any obvious sign of instability, until occasionally that energy is released, and when it is, it doesn't come out slowly. It comes out in bursts, flashes, flares, events that, for a brief moment, make an object the size of a city appear brighter than entire regions of the galaxy. Now, if we bring this back to SGR 1806-20, it becomes easier to see how something like the 2004 flare could occur. This wasn't an object that suddenly became powerful. It was already powerful. The energy was already there, stored in its magnetic field, built up over time. The flare was simply the moment when that stored energy found a way to escape. But there's still a missing piece, because knowing that energy is stored doesn't fully explain how it's released. What triggers it? What causes a stable object to suddenly produce such an intense burst? And why does it happen at one moment rather than another? Somewhere deep inside a massive star, long before anything collapses or explodes, a quiet process is already setting the stage for something far more unusual than a typical stellar ending. At that point, the star looks stable from the outside. It shines, it radiates energy, and it goes about its life in a way that would seem familiar if we could observe it over long enough timescales. But inside, things are becoming increasingly complex. Layers of fusion are building up. Different elements are forming in shells, one inside another, each requiring higher temperatures and pressures to sustain. Hydrogen becomes helium, helium becomes carbon, carbon becomes heavier elements, and so on. It's a steady progression, but also a finite one. Eventually the star reaches a point where it begins producing iron in its core, and iron, unlike lighter elements, doesn't release energy when it fuses. Instead, it absorbs it, which means the process that has been holding the star up against gravity starts to fail. The outward pressure weakens, the balance breaks, and gravity takes over. What follows happens very quickly, but will slow it down. The core begins to collapse inward under its own weight. Matter accelerates toward the center, compressing more and more tightly. Temperatures rise, densities increase, and the structure of the star changes in ways that are difficult to imagine in everyday terms. At first, atoms are squeezed closer together. Then, they begin to break apart. Electrons are pushed into protons, forming neutrons. The core becomes a dense, compact region of neutron-rich matter. And as this collapse continues, something else is happening at the same time. The star is spinning. Maybe not especially fast at first, but fast enough. And as the core shrinks, its rotation speeds up. This is a natural consequence of conservation of angular momentum, though we don't need to linger on the terminology. It's the same principle you see when something spinning becomes smaller and rotates faster. So as the core collapses from something larger than the Earth to something the size of a city, its rotation increases dramatically. What might have been a relatively slow spin becomes something much faster, sometimes incredibly fast. Now, alongside this increasing rotation, there's another feature of the star that begins to change: its magnetic field. Even ordinary stars have magnetic fields, though they're usually not particularly strong on a cosmic scale. They're generated by the movement of charged particles within the star, creating complex patterns that shift over time. But during collapse, those magnetic field lines don't disappear. They're compressed, pulled inward, concentrated, and as they are squeezed into a much smaller volume, their strength increases significantly. If the conditions are just right, this process can amplify the magnetic field to extraordinary levels. This is where the birth of a magnetar begins to diverge from the birth of a typical neutron star. Because not every collapsing core ends up with such an extreme magnetic field, there's an additional process that may come into play, something often described as a kind of dynamo effect. It's similar in concept to how magnetic fields are generated in planets like Earth, where the motion of conducting material creates and sustains a magnetic field. But here, the scale and intensity are far greater. The newly forming neutron star is hot, dense, and rapidly rotating. Inside it, matter is moving in complex ways, and these motions can further amplify the magnetic field. If the rotation is fast enough and the internal conditions are right, the field can grow to levels far beyond what we see in most neutron stars, trillions upon trillions of times stronger than Earth's magnetic field. At that point, the object crosses a threshold. It becomes something distinct, a magnetar. But this transformation isn't a single, clearly defined moment. It's more like a transition, a combination of collapse, rotation, and magnetic amplification that results in a new kind of object. And in its earlier stages, a newly formed magnetar is anything but quiet. It spins rapidly. It emits intense radiation. It sheds energy as it adjusts to its new state. Over time, that activity begins to settle, the rotation slows, the emissions become less extreme, but the magnetic field remains, and that's the key. Because while rotation can decrease and surface activity can calm down, the magnetic field is something that evolves more slowly. It doesn't just vanish, it persists, and it continues to influence the structure and behaviour of the star. Now, there's something interesting about how rare this process is. Many stars end their lives in supernova explosions. Many neutron stars are formed as a result, but only a small fraction of those become magnetars, which suggests that the conditions required for this transformation are quite specific. It's not enough for a star to be massive, it needs to have the right internal dynamics, the right rotation rate, the right environment during collapse, and even then, it's not guaranteed. So when we observe a magnetar like SGR 1806-2, we're looking at something that represents a particular outcome of stellar evolution, a path that only some stars take, and one that leads to some of the most extreme conditions found anywhere in the universe. Now, if we step back for a moment, there's a quiet continuity in all of this. A star forms, lives, and eventually collapses. Out of that collapse, something new emerges. In most cases, it's a neutron star or a black hole, but in some cases, it's a magnetar, an object that carries forward the mass of the original star, but in a completely different form, more compact, more intense, more focused. It's not the end of the star's story, it's a transformation. And that transformation sets the stage for everything that follows. Because once a magnetar exists, it begins a new kind of life. one defined not by fusion, but by magnetic energy, not by steady burning, but by occasional, unpredictable releases of stored tension. And those releases, when they happen, can be extraordinarily powerful. But before we get there, there's one more aspect worth understanding. Because while we've talked about the formation process, we haven't yet fully explored what the interior of a magnetar is like, what it means for matter to exist under such extreme pressure, how the structure of the star supports these immense forces, and why that structure can hold together, even when subjected to stresses that would destroy almost anything else. If you were to take a moment and imagine holding a small object in your hand, something simple like a pebble or a metal spoon, it would feel solid, stable, and well-defined. You could turn it over, feel its weight, notice its texture. Everything about it would seem predictable, familiar, and comfortably within the rules you've known your entire life. But that sense of familiarity depends on something we rarely think about: space. Not the vast emptiness between stars, but the tiny spaces inside matter itself. Atoms, despite sounding dense and compact, are mostly empty. A nucleus sits at the centre, surrounded by electrons that occupy regions far larger than the nucleus itself. The structure is held together by forces that create stability, but also leave room, plenty of it. That's why objects feel solid without being impossibly heavy. That's why you can hold something in your hand without it weighing as much as a mountain. Now slowly take that idea and begin to remove the empty space. Not all at once, but gradually. Imagine squeezing matter tighter and tighter, reducing the distance between particles, bringing them closer together than they would naturally prefer to be. At first, nothing too unusual happens. Materials resist compression, pushing back slightly. But with enough pressure, the structure begins to change. Atoms are forced closer. Electron clouds overlap. The distinction between one atom and another starts to blur. Push further, and electrons are no longer able to remain in their usual positions. They are driven into the nuclei of atoms, combining with protons to form neutrons. At this point, the matter you started with is no longer made of atoms in any familiar sense. It has become something else. Neutron-rich, incredibly dense and structured in a way that doesn't exist anywhere naturally on Earth. This is the kind of matter found inside a neutron star, and inside a magnetar, that compression is taken to an extreme. To understand just how extreme, it helps to step back and consider scale again, but gently, without rushing into numbers that feel too large to grasp. Picture a mountain, something massive, solid, and heavy. Now imagine compressing that mountain down into something the size of a sugar cube. Not metaphorically, but physically. All of that mass, all of that material, packed into a tiny volume. That's the kind of density we're dealing with. A teaspoon of neutron star material would weigh billions of tons, not because it's large, but because there is almost no empty space left inside it. Everything is packed together as tightly as the laws of physics will allow, and even then, those laws are being pushed to their limits. Now what's interesting is that this matter doesn't simply collapse further. It doesn't continue shrinking indefinitely. Something stops it. Not in the way a solid surface stops you when you press against it, but in a more subtle, almost invisible way. The particles themselves resist being compressed beyond a certain point, not because they push back like springs, but because of the fundamental rules governing their existence. Neutrons, like other particles, follow principles that prevent them from occupying the same exact state. When you try to compress them too closely, they resist, not through force in the usual sense, but through the structure of quantum mechanics itself. This resistance creates a kind of pressure, not mechanical, not thermal, but something deeper, and that pressure is what holds a neutron star and a magnetar together. Barely. Because gravity is still trying to pull everything inward, constantly, relentlessly. So what you end up with is a delicate balance. On one side, gravity trying to compress the star even further. On the other, quantum effects, preventing that collapse from continuing, and between them, matter exists in a state that is difficult to describe using everyday language. Now, inside a magnetar, this balance is influenced by something else as well: magnetism. The magnetic field is so strong that it doesn't just exist around the star, it interacts with the matter inside it. It places stress on the structure, it influences how particles behave, and in some ways it adds another layer of tension to an already extreme environment. Imagine for a moment a solid object under pressure, not just from being squeezed inward, but also being twisted, stretched, and pulled in different directions. That's closer to what a magnetar experiences. The crust, which we mentioned earlier, is often described as incredibly strong. In fact, it's thought to be one of the strongest materials in the universe, stronger than steel, stronger than anything we can produce. And yet, even that crust is under constant strain. Because the magnetic field is not static, it shifts, it evolves, it pulls on the star's structure in ways that are not entirely uniform. Over time, that creates stress, and that stress builds. Now, going back to the interior for a moment, there's still a lot we don't fully understand about what exists at the deepest levels of a neutron star or magnetar. Some theories suggest that under such extreme pressure, even neutrons themselves might break down into more fundamental particles. Quarks, the building blocks of protons and neutrons. If that happens, the core could contain a kind of matter known as quark matter, or something even more exotic. But this is still an area of active research. We don't have direct observations of these interiors. We rely on models, equations, and indirect measurements. So while we can describe the outer layers with some confidence, the deeper regions remain a bit mysterious, which in a way adds to the sense of scale, not just in terms of size or density, but in terms of how much there is still to learn. Now, if we shift back to something more tangible, it's worth thinking about what would happen if a small amount of this material was somehow brought to Earth. Not that this could actually happen in any practical sense, but as a thought experiment. The moment it left the intense gravitational field of the magnetar, it would no longer be stable in its compressed form. The forces holding it together would disappear, and it would rapidly expand, releasing energy as it returned to a more familiar state. In other words, it wouldn't remain a tiny, dense object. It would change dramatically. Which highlights something important. This kind of matter can only exist under very specific conditions. Remove those conditions and it no longer behaves the same way. So when we talk about magnetars, we're not just talking about dense objects. We're talking about environments where matter is held in a state that depends entirely on extreme pressure and gravity, conditions that don't exist anywhere else nearby. Now, bringing this back to the larger picture, all of this compression, all of this density, is part of what allows a magnetar to store such enormous amounts of energy. Because when matter is packed this tightly, and when magnetic fields are this strong, even small changes can release significant amounts of energy. The system is stable, but only up to a point, and that point can shift, which is why magnetars are capable of producing sudden bursts and flares. The energy isn't coming from fusion, like in a normal star. It's coming from the structure itself, from the magnetic field, from the tension stored within the star's crust and interior. And when that tension is released, even partially, the result can be extraordinary. Magnetism is one of those things that feels familiar right up until it suddenly isn't. You've probably seen it in simple forms: a magnet picking up paper clips, a compass needle aligning itself with the Earth's field, maybe even the quiet hum of electronics relying on magnetic interactions behind the scenes. It's predictable, almost gentle, something we rarely think about unless it's doing something useful. But that sense of familiarity only holds at very small scales, because magnetism, like many forces in nature, doesn't have a built-in limit that matches our intuition. Under the right conditions, it can become something far more powerful than anything we encounter in everyday life. And a magnetar is where that transformation becomes most apparent. To understand just how strong these magnetic fields are, it helps to build up slowly, starting with what we know, the Earth's magnetic field, the one that guides, compasses, and helps protect us from charged particles, is relatively weak. It's enough to influence navigation and shape the behaviour of the upper atmosphere, but it doesn't noticeably affect the objects around you in daily life. A small fridge magnet is stronger than the entire magnetic field of our planet. That might seem surprising at first, but it gives us a useful starting point. From there, we can scale up. A typical neutron star has a magnetic field that is already trillions of times stronger than Earth's. At that level, magnetism begins to dominate the behaviour of charged particles nearby. It can accelerate them to high energies, shape radiation, and create powerful emissions. But even that is not the upper limit. A magnetar goes further. Its magnetic field is about 1,000 times stronger than that of a typical neutron star. And at that level, magnetism is no longer just an influence. It becomes a defining feature of the object itself. The field is so strong that it doesn't just exist around the star like an invisible halo. It threads through the star, shapes its structure, and stores enormous amounts of energy. It's difficult to picture, so it helps to approach it from a few different angles. One way is to think about distance. If a magnetar were placed somewhere within our solar system, even at a safe distance, its magnetic field would still have noticeable effects. Not destructive in the way we usually imagine, but disruptive. Electronic systems could be affected. Data storage devices might lose their information. The arrangement of atoms in certain materials could begin to change. And all of that without the magnetar being anywhere near the Earth. That's how far-reaching its magnetic influence can be. Another way to think about it is in terms of energy. Magnetic fields carry energy. In most situations, that energy is small compared to other forms of energy we deal with. But in a magnetar, the field is so strong that it holds a vast amount of energy within it, not as heat, not as motion, but as stored potential. It's a bit like winding up a spring, except instead of a small mechanical device, you're dealing with an entire star. The field lines twist, stretch, and interact with each other, and over time, that creates tension. Now, this tension isn't something you can see directly, but its effects are very real. The magnetic field of a magnetar is not perfectly smooth or stable. It evolves, shifts, and occasionally rearranges itself. And as it does, it exerts forces on the star's crust. Imagine a network of invisible lines pulling and pushing on a solid surface. Not uniformly, but in complex patterns. Some regions experience more stress than others. Some areas are pulled in one direction, others in another. Over time, this creates strain, and that strain builds. Now, in most objects, when stress builds up, it's eventually released in some way. A material bends, cracks, or deforms. In a magnetar, the crust is incredibly strong, as we've already discussed. But even something that's strong has limits, and the magnetic field doesn't stop pushing. It continues to evolve, it continues to store energy, and eventually that energy finds a way to release itself. But before we get to that release, there's another aspect of magnetism at this scale that's worth considering, because at these field strengths, magnetism doesn't just affect matter, it can affect light. Under normal conditions, light travels through space in straight lines, unaffected by magnetic fields. But in the presence of extremely strong fields, like those around a magnetar, something unusual happens. The vacuum of space itself begins to behave differently. It's a subtle effect, but it means that light passing through such a field can change slightly, splitting into different polarization states. This phenomenon is known as vacuum birefringence. It's not something you would notice without specialized instruments, but it's a reminder that at these extremes, even the empty space around the star is not entirely passive. The field is so strong that it changes how space behaves. Now, bringing this back to SGR 1806-20, all of this magnetic energy is part of what makes the object capable of producing such a powerful flare. The energy isn't being generated at the moment of the explosion. It's already there, stored, accumulated over time, held in the structure of the magnetic field itself, and that's an important distinction. because it means that the flare is not a sudden creation of energy, but a sudden release of energy that has been building for a long time. Now, there's something quietly interesting about how this process unfolds. The magnetic field doesn't simply grow stronger and stronger without limit. It evolves. It can twist, tangle, and become more complex. And as it does, the configuration of the field becomes less stable. Think of it like a set of stretched rubber bands pulled in different directions. As long as they remain in balance, nothing happens. But if one part shifts, if the tension becomes uneven, the entire system can snap into a new configuration. And when that happens, energy is released. In a magnetar, that release can be enormous, because the amount of energy stored in the magnetic field is so large. Now, it's worth noting that this doesn't happen constantly. Magnetars spend most of their time in a relatively quiet state. They emit radiation, they rotate, they exist. And then, occasionally something changes. A shift in the magnetic field, a build-up of stress in the crust, a point where the system can no longer maintain its current configuration. And that's when we see bursts, sometimes small, sometimes large, and in very rare cases, like the one in 2004, extremely large. Now, if we step back for a moment, there's a certain balance in all of this. The same magnetic field that makes a magnetar so powerful is also what allows it to store energy over long periods. It's both the source of stability and the source of instability. It holds the system together, but it also creates the conditions for sudden change. And that dual role is what makes magnetars so interesting to study. They're not just static objects, they're dynamic, evolving, constantly adjusting, and occasionally releasing energy in ways that briefly make them some of the most luminous objects in the universe. There comes a point where even something as steady as a magnetic field can no longer remain quiet. Up until now, we've been thinking of magnetism inside a magnetar as something immense but contained. A powerful presence, yes, but one that mostly holds together, shifting slowly, storing energy, maintaining a kind of tense balance beneath the surface. But that balance isn't permanent, because the magnetic field inside a magnetar is not smooth or uniform. It's tangled, twisted, and constantly evolving. Field lines loop, cross and pull against each other in complex ways, and over time, those interactions begin to matter. Not immediately, not all at once, but gradually, almost imperceptibly, the system becomes more strained. If you imagine stretching a piece of fabric, gently at first, nothing much happens. The material holds, it adjusts. You might feel a slight resistance, but it's manageable. Keep pulling though, and the tension increases. Threads begin to take on more stress. The structure holds, but only because everything is still within its limits. Now imagine that fabric isn't being stretched evenly. Some areas are pulled harder than others, some sections twist, others compress. The tension becomes uneven, and that's where things start to change. Inside a magnetar, something similar is happening, though on a far more extreme scale. The magnetic field isn't just sitting quietly around the star, it's embedded within it, threading through the crust and interior. As it evolves, it exerts forces on the material of the star, pulling and pushing in ways that are not always balanced. And because the field is so strong, those forces are enormous. The crust of a magnetar, as we mentioned earlier, is incredibly strong. It's often described as the strongest known material in the universe, capable of withstanding pressures far beyond anything we could produce. But strength doesn't mean invulnerability. Even the strongest material can only handle so much stress. And in this case, the stress is being applied continuously, slowly building, quietly increasing. Now, there's something important about how this stress develops. It doesn't build in a straight line. It builds in patterns. Localized regions of tension, areas where the magnetic field is particularly twisted or concentrated. These regions become points of weakness, not because the material itself is weak, but because the forces acting on it are uneven. Over time, those forces begin to distort the crust. Very slightly at first, small deformations, tiny shifts. nothing that would immediately lead to a release of energy. But the system remembers those changes, the stress accumulates, and eventually something gives, not gradually, not with warning in any way we could observe directly, but suddenly the crust cracks. This is what scientists call a star quake. The term might sound familiar, and that's because it's conceptually similar to an earthquake. Stress builds up along faults, and when the material can no longer hold, it shifts abruptly, releasing energy in the process. But in a magnetar, the scale is entirely different. The forces involved are vastly greater, the energy released is far more intense, and the consequences extend beyond the immediate fracture, because when the crust cracks, it doesn't just release mechanical stress, it triggers a reconfiguration of the magnetic field. And that's where things change from a slow build-up to something much more dramatic. The magnetic field, which had been twisted and strained, suddenly snaps into a new configuration. Field lines reconnect. Energy that had been stored in the structure of the field is released all at once, and that release doesn't stay contained within the star. It propagates outward. Radiation is emitted. Particles are accelerated. A burst of energy moves away from the magnetar at the speed of light. This is the beginning of a flare. Now, the word violence might seem a bit strong, especially in a calm discussion like this, but it's useful in a specific sense. Not as something chaotic or destructive in a human context, but as a description of how quickly and intensely the system changes. Because for a long time everything is quiet, stable, tense, but contained. And then, in a fraction of a second, that tension is released. The system reorganizes itself. Energy that took years, decades, or even centuries to build up is released almost instantly. It's a shift from stillness to sudden activity, from stored energy to emitted energy, and once that process begins, it unfolds very quickly. The initial crack in the crust sets off a chain reaction. The magnetic field adjusts. That adjustment affects other regions, more stress is released, more field lines reconnect, and the entire system moves toward a new equilibrium. Now, it's important to note that this doesn't destroy the magnetar, it doesn't tear it apart or fundamentally change its existence. Instead, it's more like a reset. The star settles into a slightly different configuration, with less stored tension than before. But the magnetic field remains, the structure remains, and over time, the process begins again. Stress builds, fields evolve, and eventually another release may occur, sometimes small, sometimes large, and in rare cases like the one we've been following, extremely large. Now, if we think back to the 2004 event, this is the mechanism that likely drove it. A build-up of magnetic stress over time, a sudden fracture in the crust, a rapid reconfiguration of the magnetic field, and the release of an enormous amount of energy, all within a very short period. There's something almost rhythmic about it, even if the timing is unpredictable. A cycle of accumulation and release, quiet and then sudden, stillness followed by activity, and then stillness again. It's not something that happens often on a human timescale, but on cosmic timescales it's part of how these objects evolve. Now, one detail that often stands out is how quickly this transition occurs. From the outside, the magnetar appears stable. There's no visible warning, no gradual increase in brightness that we can observe beforehand, just a sudden spike, a flash, and then a return to relative calm, which makes these events both fascinating and challenging to study, because they don't give us much time to prepare. We observe them after they happen, using the data they leave behind, and from that data, we reconstruct the sequence of events, piece by piece. Now, as we move forward, it becomes easier to connect this mechanism to the flare itself, because what we've just described is the underlying cause, the build-up of magnetic stress, the sudden release, the reconfiguration of the field, the emission of energy. Beneath the surface of a magnetar there is no sound, no vibration in the way we would recognize, and no sense of movement that any human body could feel. And yet, under those extreme conditions, something very similar to an earthquake can occur. Not gently, not slowly, but in a way that releases more energy than anything we experience on Earth. To understand how a star can crack, it helps to begin with the idea that even something as dense and extreme as a neutron star still has structure. It isn't just a uniform sphere of matter, it has layers, and the outermost of those layers behaves, in some respects, like a solid crust. Of course, calling it solid doesn't quite capture what it is. This crust is made of incredibly dense material, compressed far beyond anything we can reproduce. The atoms are packed tightly together, arranged in a lattice that is both rigid and immensely strong. If we could somehow compare it to materials we know, it would surpass them all. Steel, diamond, any alloy we've created, none of them come close. The crust of a neutron star is often described as the strongest known material in the universe. But strength, even at that level, has limits. And inside a magnetar, the forces acting on that crust are unlike anything we encounter elsewhere. The magnetic field threads through the star, pulling and twisting, in ways that are not evenly distributed. Some regions experience more strain than others. Over time, those differences begin to matter. Stress accumulates, not quickly, not dramatically, but steadily. If you imagine a large sheet of ice on a frozen lake, it may look perfectly still from above, smooth, quiet, unchanging. But beneath that calm surface, pressure can build. Temperature shifts, subtle movements, and uneven forces create tension within the ice. And then, at some point, a crack forms. It can happen suddenly, without warning, and when it does, the sound carries across the entire surface. In a magnetar, the process is similar in concept, but far more intense. The crust is under constant stress from the magnetic field. It resists holding its structure, but only up to a certain point. As the field evolves, the strain increases, especially in regions where the field lines are more twisted or concentrated. Eventually, the material reaches its limit, and when it does, it breaks, not gradually, not with a slow deformation, but with a sudden fracture. This is what scientists refer to as a starquake. Now, unlike an earthquake, there's no ground to shake in the way we experience it. There's no air to carry sound waves, no surface for vibrations to travel across in a way we could perceive directly. But the energy release is real, and it's enormous. When the crust cracks, it shifts. Sections of it move relative to each other, releasing the stress that had been building up. That movement, even if it's only a small fraction of a meter, involves an incredible amount of energy because of the forces at play, and that's only the beginning. Because the crust isn't isolated from the rest of the star, it's connected to the magnetic field, so when the crust shifts, it forces the magnetic field to adjust. Field lines that were stretched and twisted are suddenly reconfigured. They snap into new positions, and as they do, they release energy. A lot of energy. This process is sometimes compared to magnetic reconnection, where magnetic field lines break and reconnect in a different arrangement, converting stored magnetic energy into radiation and particle motion. It's a bit like stretching a set of elastic bands until they suddenly slip and snap into a new configuration. Except here, the elastic bands are magnetic field lines, and the energy involved is on a cosmic scale. Now what's interesting is that these starquakes can vary in size. Some are relatively small, releasing modest amounts of energy and producing brief bursts of radiation. These are the kinds of events that led to the classification of objects like SGR 1806-2 as soft gamma repeaters in the first place. Short repeating bursts, unpredictable but not extreme. But every now and then the conditions align for something much larger. A larger region of the crust is under stress, a greater amount of magnetic energy has been stored, and when the fracture occurs it involves a much larger portion of the star. That's when a giant flare can happen, the kind of event we've been building toward. Now there's a subtle detail here that's worth noticing. The crust doesn't just crack once and then stop. The initial fracture can trigger additional shifts. One region moves, which affects another, which then releases more stress. It's a cascade, a chain reaction of adjustments that propagate through the star's structure and magnetic field. And all of this unfolds very quickly. From our perspective, it appears as a sudden spike in radiation, but internally, it's a complex sequence of events: crust breaking, magnetic field reconfiguring, energy being released in multiple stages. Now, if we think about the scale of these starquakes, it becomes a bit easier to connect them to the flare we observed in 2004. Because the energy released during that event wasn't just the result of a single crack, it was the result of a large-scale reconfiguration of the Magnetar's magnetic field, triggered by a significant fracture in its crust. The star didn't shatter, it didn't come apart, but it did shift, and that shift was enough to release an enormous amount of stored energy. There's something quietly remarkable about that. An object so dense, so strong, and so stable, and yet capable of undergoing sudden changes that release energy on a scale that briefly rivals entire galaxies. It's a reminder that stability doesn't mean stillness. Even the most rigid systems can change, and when they do, the effects can be far-reaching. Now, another interesting aspect of starquakes is how they relate to the rotation of the magnetar. After a quake, the rotation rate can change slightly. Not by much, but enough to be measured. It's similar to how an earthquake on Earth can slightly alter the length of a day by redistributing mass. In a magnetar, these changes are more subtle, but they provide valuable clues about what's happening inside. By measuring how the rotation shifts, scientists can infer details about the structure of the star and the nature of the quake. It's a way of learning about something we can't observe directly. Now, bringing this back to the broader picture, starquakes are the mechanism that links the internal dynamics of a magnetar to the radiation we detect. They are the bridge between stored magnetic energy and emitted gamma rays. Without them, the energy might remain locked within the star, but with them, that energy has a pathway to escape. And when it does, it travels outward, carrying information about the conditions that produced it. Once the crust has shifted and the magnetic field has snapped into a new configuration, the energy that was stored inside the magnetar doesn't linger for long. It moves outward, not slowly, not in a gradual release, but in a rapid surge that transforms that internal adjustment into something we can detect across the galaxy. What leaves the star in that moment isn't heat in the usual sense, and it isn't visible light like the glow of a normal star. Instead, it emerges as gamma rays, the most energetic form of electromagnetic radiation. Now, gamma rays are still light, technically speaking. They travel at the same speed as all other forms of light, but they carry far more energy per photon, which means that even a small amount of gamma radiation can represent a significant release of energy, and when a magnetar produces a flare, it doesn't emit just a small amount. It releases a concentrated burst. Now, to understand how this works, it helps to imagine what happens immediately after a starquake. The crust cracks, the magnetic field reconfigures, and as those magnetic field lines snap and reconnect, they accelerate charged particles around the star. Electrons and other particles are suddenly pushed to extremely high energies, moving along the magnetic field lines at speeds approaching that of light. As they move, they emit radiation, high-energy radiation, gamma rays. At the same time, the rearrangement of the magnetic field itself releases energy directly into the surrounding space. So what you end up with is not a single, simple emission, but a combination of processes all contributing to the same result. A burst of gamma radiation expanding outward from the magnetar. Now, this burst doesn't spread evenly in all directions in a perfectly uniform way. There are structures within it, patterns, variations in intensity. But on a large scale, it still expands outward like a rapidly growing sphere, carrying energy away from the source at the speed of light. And because gamma rays interact less with matter than lower energy forms of light, They can travel vast distances through space without being significantly absorbed or scattered, which is why, even after travelling for tens of thousands of years, the flare from SGR 1806-20 was still detectable when it reached Earth. Now, there's a useful distinction to make here. Not all gamma-ray events are the same. You might have heard of gamma-ray bursts, often abbreviated as GRBs. These are some of the most powerful explosions in the universe, typically associated with collapsing massive stars or the merging of neutron stars. They can last from a fraction of a second to several minutes, and they often originate in distant galaxies. Magnetar flares, like the one from SGR 1806-20, are different. They're usually shorter. They originate from known objects within our own galaxy, and they're driven by magnetic processes rather than by large-scale collapse or collision. That said, in terms of intensity, the largest magnetar flares can briefly rival some of the most powerful gamma-ray bursts, which is part of what made the 2004 event so remarkable. Now, if we slow things down and look at the structure of a typical magnetar flare, it unfolds in stages. The first stage is the initial spike. This is the most intense part of the event. It rises rapidly, peaks within a fraction of a second, and then drops off. During this brief moment, the energy output is at its highest. This is the part that overwhelmed detectors and stood out so clearly in the data. Following that initial spike is a longer-lasting tail. This tail can last for several minutes, gradually decreasing in intensity, but it's not a smooth fade. It often shows a repeating pattern, pulses, regular variations in brightness. These pulses are tied to the rotation of the magnetar. As the star spins, regions of emission sweep past our line of sight, creating a pattern similar to a lighthouse beam rotating across the horizon. Each time the beam points toward Earth, we detect pulse. And because the rotation period of the magnetar is known, these pulses can be used to confirm the identity of the source. In the case of SGR 1806-20, this pulsing tail provided additional evidence that the flare originated from that specific object. Now, there's something quietly interesting about how concentrated the energy release is during the initial spike. Most of the total energy is released in that very short window, less than a second, and yet that brief moment dominates the entire event. It's like a sudden flash that defines everything that follows. Now, if we think about how this energy travels, it helps to remember that space is mostly empty. There's very little to slow the gamma rays down, so once they're emitted, they move outward freely, spreading over larger and larger distances. As they spread, the energy is distributed over a wider area, which means that by the time the flare reaches Earth, the energy per unit area is much lower than it was near the source. That's why, despite the immense energy released, the effect on Earth is subtle, but the signal itself remains detectable. Now, one detail that often stands out is how brief these events are. A fraction of a second for the peak, a few minutes for the tail, and then it's over. But the implications of that brief event can be studied for years, because the data it provides is rich with information. By analysing the spectrum of the gamma rays, scientists can learn about the processes that produced them. By studying the timing of the pulses, they can refine measurements of the magnetar's rotation. And by comparing this flare to others, they can build a broader understanding of how magnetars behave. Now, bringing this back to the idea of cosmic blasts, it's worth noting that the word blast can be a bit misleading. In everyday terms, we think of a blast as something that produces a shockwave in air or another medium, something that pushes outward with force. In space, there's no air to carry such a wave, so the blast is not a shockwave in the traditional sense. It's a burst of radiation, energy moving outward as light, and while that might sound less dramatic, it's no less significant. Because radiation can carry enormous amounts of energy, even without a physical medium to push through. Now, if we take a moment to reflect on the scale of what we've been describing, there's a certain contrast that stands out. On one hand, the event is incredibly brief. On the other, it involves an amount of energy that is difficult to fully grasp. A fraction of a second. Hundreds of thousands of years' worth of solar output, both true at the same time. and that combination is part of what makes magnetar flares so fascinating. They compress vast amounts of energy into very short timescales. They take something that would normally unfold slowly and release it almost instantly. The giant flare from SGR 1806-20 in 2004. We've touched on its intensity, we've described its general structure, but there are details worth exploring more carefully. How exactly it unfolded, what the data showed, and why it stands out even among other magnetar flares. December 27th, 2004 began like any other day on Earth. There was no warning in the sky, no change in the air, no visible sign that one of the most powerful events ever detected was about to make itself known. People were waking up, moving through routines, travelling, resting, talking, eating, and doing all the ordinary things that fill a day. Meanwhile, far above the surface, satellites were quietly doing what they always do, collecting data, monitoring radiation, and watching parts of the universe that human eyes will never directly see. Then, without any ceremony at all, the signal arrived. Not gradually, not as a slow rise, not as something that gave the instruments time to adjust. It came as a sudden spike in gamma rays, so intense that several detectors were immediately overwhelmed. For a tiny fraction of a second, the incoming signal was simply too strong for some instruments to measure properly. That alone tells you a great deal. These were not fragile devices, and they were built specifically to observe energetic cosmic events. Yet this flare hit them hard enough that, for an instant, the event exceeded their comfortable working range. To understand what happened that day, it helps to slow the whole thing down and separate it into pieces. The flare itself was brief, but not simple. It had structure, it had stages, and like many cosmic events, it only looks instantaneous until you begin examining the details. The first and most important part was the initial spike. This was the moment of maximum intensity. It rose extremely fast and peaked in about 1/10 of a second. That is almost no time at all in human terms. It is shorter than a blink, shorter than the pause between one thought and the next, and yet in that tiny sliver of time, SGR 1806-20 released an extraordinary amount of energy. Scientists later estimated that the flare emitted, in that brief opening phase, more energy than the Sun gives off in roughly 150,000 years. That number is so large that it risks becoming abstract, so let's keep it grounded. The Sun is not a weak object. Every second it radiates an immense amount of energy in every direction. It has done so for billions of years, and it will continue for billions more. It powers life here, drives our climate, lights our skies, and quietly sustains the entire solar system. To say that a city-sized object released the equivalent of 150,000 years of solar output in a fraction of a second is not just to say it was energetic. It is to say that the event belongs in a category of extremes that is difficult to compare to anything nearby. And still, the truly interesting part is not just how much energy was released, but how it was released. Because this was not a supernova. It was not a star tearing itself apart permanently. It was not the birth of a black hole. It was a magnetar flare, triggered by a sudden and violent reconfiguration of one of the strongest magnetic fields in the universe. Inside SGR 1806-20, magnetic stress had likely been building for a long time. The star's crust, incredibly rigid and dense, was under strain. The magnetic field was twisted, distorted, and storing enormous energy. At some point, the stress exceeded what the crust could tolerate. A fracture occurred. A starquake began. The crust shifted. The magnetic field snapped into a new arrangement. And in that sudden adjustment, energy that had been stored over years or perhaps much longer was released almost instantly. That release produced the initial spike. Now, if the story ended there, the flare would still be remarkable, but it didn't end there. After the opening burst came a longer phase, a fading tail that lasted several minutes. This part of the event was much less intense than the first spike, but it was still enormously important. As the flare faded, instruments detected a repeating pattern. The brightness rose and fell in pulses, regular and steady like a rhythm. Those pulses matched the rotation period of the magnetar. SGR 1806-20 rotates roughly once every 7.5 seconds. As it spun, regions of hot plasma and trapped radiation associated with the flare swept across our line of sight again and again. This created the pulsed tail. In other words, after the initial eruption, the magnetar continued to radiate as it rotated, almost like a cosmic lighthouse turning slowly in the dark. This part of the signal helped scientists confirm the source with much greater confidence. The pulse period matched what was already known about SGR 1806-20, so the flare was not just a mystery spike in the sky, it was clearly tied to a specific object with known behaviour. That matters because the universe is full of energetic events, and they do not all come from the same mechanism. A giant flare from a magnetar has a different fingerprint from a gamma-ray burst, caused by a collapsing massive star or a merger of neutron stars. The repeating tail gave the event a very clear identity. Another detail worth slowing down for is the sheer brightness of the initial flash. If human eyes were sensitive to gamma rays, the flare might have appeared brighter than the full moon despite being about 50,000 light-years away. That comparison is slightly strange, but useful. The full moon is close, obvious, and bright enough to cast shadows on Earth. SGR 1806-20 was on the far side of our galaxy, buried in a dense region of space, and yet its gamma-ray flare was so powerful that, in its own part of the spectrum, it briefly rivaled that level of apparent brightness. That tells you something important about proximity and power working together. There are gamma-ray bursts far more energetic in total output than this giant flare, but they usually occur in distant galaxies. They're far away enough that, by the time their light reaches us, their signal has weakened enormously. SGR 1806-20 was different. It was close enough in cosmic terms to hit our instruments with unusual strength, and this is where the 2004 flare becomes especially valuable scientifically. Because the event was nearby, it could be studied in much greater detail than many more distant explosions. Researchers could compare data from multiple satellites. They could examine the shape of the initial spike, the spectral evolution of the flare, the timing of the pulse tail, and the atmospheric effects on Earth. The flare became not just an extreme event, but a useful one. Now, let's stay with the initial spike a little longer, because this is where much of the drama sits. When the signal hit the satellites, some detectors saturated almost instantly. Saturation means the incoming signal was stronger than the detector could cleanly measure. Imagine trying to weigh something with a kitchen scale, only to find the object is so heavy that the display maxes out and refuses to tell you the true value. That is roughly what happened with some instruments. The flare was so intense that it briefly exceeded their design assumptions. Fortunately, not all instruments responded the same way. Different satellites had different detector types, different sensitivities, different orientations, and different energy ranges. By combining the surviving measurements and comparing data across multiple platforms, scientists were able to reconstruct what had happened with considerable precision. This is one of those quiet triumphs of observational science that often gets overlooked. No single instrument tells the whole story. It is the combination that matters. One detector may saturate but still provide timing information. Another may miss some of the peak but capture the tail beautifully. A third might help with localization, and when the pieces are assembled carefully, a fuller picture emerges. That fuller picture showed a classic giant flare profile, a sudden, enormously bright spike, a fading tail, regular pulsations tied to the rotation of the neutron star, and an energy release unlike anything else of its kind ever recorded. It also showed that the flare interacted, however subtly, with Earth. This is one of the most quietly astonishing parts of the story. By the time the radiation reached our planet, it was spread out over an enormous area. Space had diluted it, distance had softened it, and yet it was still strong enough to measurably disturb Earth's ionosphere, the upper layer of the atmosphere filled with charged particles. There were slight changes in ionization. There were small disturbances in very low-frequency radio propagation. Nothing dramatic enough to affect daily life for most people, but absolutely enough to leave a scientific footprint. That means the event did not merely pass by Earth as a piece of distant information. It physically interacted with the planet's atmosphere. A flare from across the galaxy, released before recorded human civilization had even begun, arrived here at a specific moment in 2004 and gently altered the upper atmosphere in ways we could measure. There is something wonderfully strange about that. It gives the event a kind of closeness without making it threatening. We were not spectators only. We were, in a very faint sense, participants. Our atmosphere felt it. Our instruments recorded it. Our planet responded. Another useful way to understand the flare is to compare it with smaller magnetar activity. Before 2004, SGR 1806-20 was already known as a soft gamma repeater. It had produced bursts before, but those were much weaker. Short flashes, manageable events. Interesting certainly, but not in the same league as the giant flare. This tells us that magnetars do not live permanently in their most extreme mode. Most of the time, they are comparatively quiet, releasing small bursts here and there as magnetic stress adjusts in modest ways. A giant flare is different. It is not just more of the same. It is a large-scale reconfiguration, a major release, a moment when the internal magnetic structure of the star shifts enough to unleash an enormous amount of stored energy all at once. That distinction matters because it suggests threshold behavior. The magnetar can absorb, store, and redistribute stress for long periods, and then suddenly cross a line where the release becomes much larger. It is the difference between a minor settling of a surface and a major fracture. The 2004 flare appears to have been one of those major fractures. And from the data, scientists learned another interesting detail. Even after releasing such an immense burst, the magnetar remained intact. It continued to rotate. It continued to emit. It was changed, certainly, but not destroyed. That tells us something about the durability of these objects. They live under extreme conditions all the time. Their crusts are under enormous stress. Their magnetic fields are beyond ordinary comparison. Their matter exists in a state that cannot be reproduced in any laboratory. And even when one of them releases a giant flare, the star itself remains. This is one reason magnetars are so compelling. They are both fragile and durable at once. Fragile because their crusts can crack and their fields can reconfigure. Durable because they survive these enormous internal adjustments and continue on. Now, when researchers examined the 2004 data, they also considered geometry. Was the flare emitted in all directions equally? Or was some of the radiation beamed more strongly in certain directions? This is an important question because it affects how we estimate the total energy released. If the flare is perfectly isotropic, meaning it radiates the same in every direction, then the observed brightness implies one total energy. If it is beamed or focused, the total energy might be somewhat lower even though the signal reaching us was very strong. The details are complicated, and not every uncertainty has been completely settled. But what remains clear is that, regardless of geometry, the flare was extraordinary. It was still the brightest giant flare ever observed from a magnetar. It was still intense enough to affect Earth's upper atmosphere, and it still stands as the strongest explosion ever detected from this class of object. That phrase, the most powerful explosion ever detected, is worth handling carefully. In astronomy, wording matters. There are supernovae and gamma-ray bursts that may release more total energy overall, but in terms of the signal detected from a magnetar giant flare, and in terms of the sheer intensity recorded from that source, SGR 1806-20 remains exceptional. It became the benchmark against which other giant flares are compared, and in a calm way that is part of what makes the event so satisfying to study. It is extreme, yes, But it is also structured. It is not random chaos. There is an internal logic to it. Stress builds, the crust fractures, the magnetic field rearranges, the initial spike is released, a trapped fireball of plasma and radiation produces the pulse tail, the star rotates, the signal fades, the atmosphere of Earth registers a faint response, data is collected, understanding grows. Everything we have discussed so far about magnetars comes together in that one event. The density of neutron star matter, the extraordinary magnetic field, the build-up of stress in the crust, the sudden release during a star quake, the emission of gamma rays, the pulsed afterglow tied to rotation, the effect on instruments and atmosphere, it all converges on December 27, 2004. And because this event was observed by multiple spacecraft, it also became a reference point for interpreting other signals. Some short gamma-ray bursts seen in distant galaxies may, in a few cases, actually be giant magnetar flares like this one, just much farther away. The 2004 event gave astronomers a template, a clearer idea of what such flares look like when seen up close by cosmic standards. That is one of the quiet gifts of rare events in science. They do not just teach us about themselves, they help us understand other events we have already seen, and events we may see in the future. If we pause for just a second and look at the whole sequence, it is almost oddly compact. A city-sized dead star, a magnetic field beyond ordinary comprehension, stress building over time, a fracture, a flash lasting a fraction of a second, a tail pulsing for minutes, a signal travelling 50,000 years, a handful of satellites recording it, Earth's atmosphere responding faintly, and from all that, a deeper understanding of how some of the most extreme objects in the universe behave. That is the flare, explained slowly. Not a mysterious blast appearing out of nowhere, but the result of a physical system reaching its limit and then releasing stored energy with astonishing efficiency. And from here, it becomes natural to ask a broader question. How large was that release really, when placed beside other things we know? How do we compare it to the Sun, to supernovae, to the output of galaxies, and to the energy scales that make sense to us? Looking at the 2004 flare in isolation already feels impressive, but placing it beside other sources of energy makes its scale easier to appreciate in a grounded way. Because without comparison, numbers like 150,000 years of solar output can start to lose meaning. They sound large, but they don't always translate into something intuitive. So instead of holding on to that number alone, it helps to gently set it next to things we already understand. Start with the Sun again. Every second, the Sun releases an enormous amount of energy, steadily and predictably. It's the baseline for almost everything we experience. Daylight, warmth, climate, and life itself all depend on that continuous flow. It doesn't surge or spike in dramatic ways. It simply continues, second after second. Now imagine pausing that steady output and compressing a vast portion of it into a single instant. That's what the magnetar flare did. Not over minutes, not over hours, but in less than a second. That contrast is where the scale becomes clearer. It's not just about how much energy was released, but how quickly it was released. A slow output, even if large, feels different from a sudden burst. The magnetar flare took something that normally unfolds over immense stretches of time and condensed it into a moment so brief that it would be easy to miss if you weren't looking for it. Now, if we expand the comparison a little further, we can look at other cosmic events. Supernovae, for example, are among the most energetic explosions in the universe. When a massive star reaches the end of its life and collapses, the resulting explosion can briefly outshine entire galaxies. It releases energy over a period of days or weeks, spreading light and matter outward across space. Gamma-ray bursts, especially those associated with collapsing stars or merging neutron stars, can be even more intense, at least in terms of peak brightness. They can release enormous amounts of energy in short periods, often focused into narrow beams. So where does the SGR 1806-20 flare fit into this picture? It doesn't quite match the total energy output of the largest supernovae or the most powerful gamma-ray bursts. But it does something different. It concentrates a huge amount of energy into a very short time, and it does so from a relatively small object. That combination makes it stand out. A city-sized remnant, producing a burst that briefly rivals the brightness of far larger systems. Now, there's another aspect worth considering: distance. Because energy alone doesn't determine how an event is experienced or detected. Distance plays a crucial role in how that energy spreads out and how intense it appears to an observer. The flare from SGR 1806-20 occurred about 50,000 light-years away. That's roughly half the diameter of the Milky Way. To put it another way, the signal travelled for 50,000 years before reaching Earth. It left its source long before recorded human history, long before cities, long before written language, and only arrived in 2004. During that journey, the energy spread out in all directions, covering an ever-growing sphere. By the time it reached us, it was diluted, softened, reduced in intensity per unit area. And yet, even after that immense journey, it was still strong enough to stand out clearly in our instruments. That's where the phrase, "felt across the galaxy," becomes meaningful, even if we keep it grounded. The flare didn't send a shockwave through space in the way an explosion does in air. There's no medium for that kind of wave to travel through. Instead, it sent out radiation, energy carried by light, and that radiation travelled across a significant portion of the galaxy. Any object in its path would have been exposed to it. Most would not have noticed in any meaningful way, just as Earth didn't experience anything dramatic. But sensitive systems, whether natural or artificial, would have registered its presence. It's a quiet kind of reach, not destructive, not overwhelming, but far-reaching. Now, if we imagine moving closer to the source, the experience would change, not abruptly, but gradually. Closer regions of space would have received a stronger signal. Stars, gas clouds, and other objects within a certain range would have been exposed to higher levels of radiation. Still, even then, it wouldn't behave like a traditional explosion pushing matter outward. It would remain a burst of radiation spreading outward, interacting with whatever it encountered. And that interaction depends on distance. Very close to the magnetar, the effects would be more pronounced. Farther away, they become subtle. At Earth's distance, they were detectable but not disruptive. Now, there's something interesting about how this event fits into the broader structure of the galaxy. The Milky Way is not empty. It's filled with stars, gas, dust, and various forms of radiation. Events like supernovae and flares occur from time to time, each contributing to the overall energy environment of the galaxy. Most of these events go unnoticed by us unless we're specifically looking for them, but occasionally one stands out, not because it's entirely unique, but because it's close enough and strong enough to be clearly observed. The 2004 flare was one of those moments. It didn't reshape the galaxy. It didn't alter the motion of stars or the structure of the Milky Way. But it did provide a clear signal, one that allowed scientists to study a magnetar in a way that would not have been possible if the event had occurred much farther away. And that's part of what makes it valuable. It's not just about the energy released. It's about the opportunity to observe, to measure, to learn. Now, if we bring this back to a more personal scale for a moment, there's a subtle contrast that emerges. On one hand, the event is immense, galaxy spanning in its reach, involving energies far beyond anything we encounter in daily life. On the other hand, its effect here was almost imperceptible. No visible change, no direct sensation, just a brief disturbance in instruments and a faint ripple in the upper atmosphere. It's a reminder that scale can be deceptive. Something can be incredibly large and still feel small from a distance, and something can be very close and feel significant even if it's relatively minor. Now, Another way to think about the flare is in terms of timing. It happened once, at a specific moment, and then it was over. The initial spike lasted less than a second. The tail lasted a few minutes, and then the magnetar returned to its quieter state. But the signal continued travelling. It moved outward, crossing space, passing by stars, gas clouds, and eventually reaching us. And that journey took tens of thousands of years. So in a sense, what we detected in 2004 was not a current event. It was a message from the past, a record of something that had already happened long ago. And that's true for all astronomical observations, but events like this make it especially clear. We're not just observing distant objects, we're observing their history. Now, if we take one more step back, there's a broader pattern here. The universe produces events across a wide range of scales. Small, frequent bursts, large, rare explosions, slow processes that unfold over billions of years, and sudden releases that last less than a second. The magnetar flare sits in a particular place within that spectrum. Not the largest in total energy, not the most frequent, but one of the most intense in terms of how quickly it releases energy and how clearly it can be detected when conditions are right, and that combination is what makes it stand out. Sometimes the easiest way to understand something very distant is to bring it a little closer, not physically, but in imagination. Up to this point, everything we've discussed has taken place at a comfortable distance. Tens of thousands of light years is more than enough space for even the most powerful events to soften before they reach us. By the time the flare from SGR 1806-20 arrived, it was strong enough to measure, but gentle enough to pass unnoticed by everyday life. But distance is doing most of the work there, so it's worth asking calmly and carefully what would change if that distance was smaller. Not dramatically smaller, just closer. Because the behaviour of the flare itself would not change. The magnetar would still release the same amount of energy in the same brief burst through the same processes we've already explored. What changes is how that energy spreads out before it reaches a given point. When energy radiates outward in all directions, it becomes more diluted the farther it travels. The same amount of energy is spread over a larger and larger area, which means the intensity at any single point decreases with distance. So if you reduce the distance, you increase the intensity. Not by a small amount, but quite significantly. Now, rather than jumping straight to extreme scenarios, it helps to move in steps. Let's imagine the flare occurring not 50,000 light years away, but perhaps a few thousand light years away. Still distant. Still far beyond any immediate concern, but closer by an order of magnitude. At that range, the signal reaching Earth would be noticeably stronger. The ionosphere would experience a larger disturbance. Radio communication might be affected more clearly. Sensitive instruments would register a more pronounced response. But even then, the atmosphere would still provide protection, absorbing much of the incoming radiation. The effect would remain primarily in the upper layers of the atmosphere, not something that directly impacts daily life on the surface. Now, moving a little closer again. Suppose the event occurred within a few hundred light years. This is where the differences begin to feel more tangible. The burst of gamma rays would arrive with much greater intensity. The ionosphere would be more strongly ionized, and the disturbance could be more widespread and longer lasting. There might be temporary disruptions in certain types of communication systems. High-altitude regions would experience increased radiation levels. Still, even at this distance, the Earth's atmosphere continues to act as a shield. Life on the surface would remain largely unaffected. The key idea here is that the atmosphere absorbs a significant portion of high-energy radiation before it can reach the ground. So even when the incoming signal is stronger, the protection remains. Now, if we continue this thought experiment and move even closer, the situation becomes more complex. At distances on the order of tens of light years, the intensity of the gamma radiation would be much higher. The upper atmosphere would absorb a large amount of energy, leading to more substantial changes in ionization. This could affect the ozone layer, which plays a role in filtering ultraviolet radiation from the sun. Changes in the ozone layer would not be immediate in their effects, but they could influence how much solar radiation reaches the surface over time. Again, this is not something that would unfold instantly. It would be a gradual consequence of how the atmosphere responds to the incoming energy. And even here, it's important to stay grounded. Events like this occurring at such close distances are extremely rare. Magnetars themselves are rare. Giant flares are even rarer, and the likelihood of one occurring very close to Earth is low. But exploring the scenario helps clarify how distance shapes the impact of cosmic events. Now, there's another aspect worth considering: direction. Not all flares are perfectly uniform in how they emit energy. Some may have regions of stronger emission depending on how the magnetic field reconfigures and how particles are accelerated. If a stronger portion of the emission were directed toward a particular region, that region would receive a higher intensity signal. But even in those cases, the overall behaviour still follows the same principle. Energy spreads out, distance reduces intensity, and the atmosphere provides protection. Now, stepping back from the details, there's a broader pattern that becomes clear. The universe is filled with energetic events. Some are far more powerful than the magnetar flare we've been discussing. Supernovae, gamma-ray bursts and other phenomena release enormous amounts of energy, but most of them occur at distances where their effects are softened long before they reach us. That's why we can observe them safely. That's why they appear as points of light or brief signals rather than immediate experiences. Distance is not just space, it's protection. Now, returning to the idea of SG 1806-20, its flare in 2004 represents a kind of balance. It was close enough to be clearly detected, strong enough to stand out among other events, but far enough away that its effects remained subtle, a measurable disturbance rather than a disruptive one. And that balance is what makes it such a valuable case study. It allows us to see how extreme physics operates without placing us directly in its path. Now, there's something quietly reassuring about that. The universe is capable of producing events of immense scale and intensity, but it also provides distance, space, separation, and within that separation, we have the opportunity to observe, to measure, and to understand, without being overwhelmed. Now, if we bring this back to a more reflective perspective, it highlights something about how we experience the universe. Most of what happens out there does not happen here. It unfolds at distances that are difficult to imagine, over timescales that stretch far beyond our daily lives. And yet, through observation, we can still connect with those events. We can detect their signals. We can interpret their patterns. We can build a picture of what's happening even when it's far away. So when we ask what would happen if an event like this occurred closer, the answer is not a single dramatic outcome. It's a range of possibilities shaped by distance, direction, and the nature of the event itself. And in the case of SGR 1806-20, the distance was just right for us to learn from it, to see it clearly, to measure it precisely, and to understand step by step how something so small can briefly become one of the most powerful sources of energy we've ever detected. High above the surface of the Earth, long before anyone noticed anything unusual, a quiet network of instruments was already paying attention. Not in the way a person watches the sky, but in a steady, continuous way. Sensors tuned to parts of the universe we cannot see were always active, always collecting data, always ready to register something out of the ordinary. They don't sleep, they don't blink, and they don't get distracted. They simply observe. And on that day in 2004, that quiet vigilance made all the difference. Because the flare from SGR 1806-20 was not something you could catch with your eyes. It didn't produce visible light in a way that would stand out in the sky. Even if you had been looking directly at its location, you would have seen nothing unusual. The signal arrived in gamma rays, and gamma rays require very specific tools to detect. Now, it helps to take a moment to understand what makes gamma rays different from the light we're familiar with. Visible light is just one small part of the electromagnetic spectrum. It's the part our eyes evolved to detect, shaped by the conditions on Earth. But beyond that narrow band, there are many other forms of light, each with different energies and properties. Gamma rays sit at the high energy end of that spectrum. They carry far more energy than visible light, and because of that they interact with matter in different ways. They can pass through materials that would block other forms of light, and they can deposit energy deep inside detectors designed to capture them. But they also present a challenge. The Earth's atmosphere absorbs gamma rays very effectively, which is a good thing for life on the surface because it protects us from constant exposure to high-energy radiation. But it also means that if you want to observe gamma rays from space, you can't do it from the ground. You have to go above the atmosphere. That's where satellites come in. Orbiting Earth, these satellites carry instruments specifically designed to detect high-energy radiation. They don't rely on lenses or mirrors in the same way optical telescopes do. Instead, they use detectors that can register the arrival of individual gamma-ray photons. When a gamma ray enters one of these detectors, it interacts with the material inside, producing a signal that can be measured and recorded. Each detection carries information, the energy of the photon, the time it arrived, sometimes even clues about its direction. Now, under normal conditions, these detectors are recording a steady background of events. Cosmic radiation, occasional bursts, random signals, nothing too dramatic. But they are always ready for something unusual, and when the flare from SGR 1806-20 arrived, it was very unusual. Multiple satellites detected it almost simultaneously. That's one of the first clues that something significant has happened. When instruments in different locations, operated by different teams, all register a sudden spike at nearly the same time, it's unlikely to be a local glitch or a technical issue. It's a real event. Now, because these satellites are spread out in different orbits, they don't all receive the signal at exactly the same instant. The differences are tiny, fractions of a second, but they are measurable. And those tiny differences are incredibly useful. By comparing the arrival times of the signal at different satellites, scientists can determine the direction it came from. It's a method known as triangulation. In simple terms, if you know when a signal reached multiple locations, and you know where those locations are, you can work backward to find the origin. It's similar to how your brain uses the slight difference in sound arrival between your ears to figure out where a noise is coming from. Except here, the ears are satellites orbiting thousands of kilometers apart, and the sound is a burst of gamma rays traveling at the speed of a light. Now, there's another layer to this process. Different satellites are sensitive to different energy ranges. Some are better at detecting lower energy gamma rays. Others are designed for higher energies. Some can handle very intense signals without saturating. Others are more sensitive but can be overwhelmed by extremely strong bursts. So when an event like the 2004 flare occurs, each instrument captures a slightly different piece of the puzzle. One might record the initial spike very clearly. Another might saturate during the peak but capture the tail. A third might provide precise timing information. And when all of that data is combined, it creates a much more complete picture than any single instrument could provide on its own. In the case of SGR 1806-20, this combination of data was essential, because the initial spike was so intense that some detectors were briefly overwhelmed. They simply couldn't measure the full strength of the signal. But other instruments, with different sensitivities, were able to capture enough information to reconstruct what had happened. Now, once the direction of the signal was determined, scientists could look at that region of the sky and compare it with known sources, and that's when SGR 1806-20 came into focus. It was already catalogued, already studied, already known to produce smaller bursts. So when the giant flare was traced back to that location, it provided a clear identification. This wasn't a new object. It was a known magnetar behaving in a way that had not been observed at this scale before. Now, beyond simply detecting the flare, the instruments also recorded its structure. The initial spike, the fading tail, the pulsed emission tied to the Magnetar's rotation. All of these details were captured in the data, and each one adds to our understanding. For example, the timing of the pulses in the tail allowed scientists to confirm the rotation period of the magnetar. The energy distribution of the gamma rays provided clues about the processes that produced them. The overall shape of the flare helped refine models of how magnetic energy is released in these objects. Now, there's something quietly elegant about this process. The event itself was brief. Less than a second for the peak, a few minutes for the tail, and then it was over. But the data it produced can be studied for years, decades even, because every photon that was detected carries information, and by analysing that information carefully, scientists can reconstruct events that happened tens of thousands of years ago and far beyond our direct reach. It's a kind of time travel in a sense, not in the way we usually imagine, but in the sense that we're observing the past through signals that have taken time to reach us. Now, there's one more aspect of detection that's worth mentioning: redundancy. The fact that multiple satellites detected the flare independently is not just useful for triangulation, it also provides confirmation. When different instruments, built by different teams, operating in different conditions, all record the same event, it strengthens the reliability of the observation. It reduces the chance that what we're seeing is an artifact or an error. And in science, that kind of confirmation is essential. Now, if we step back and look at the broader picture, it becomes clear that events like the 2004 flare are not just about what happens out there. They're also about what we have here. The tools we've built, the systems we've put into orbit, the methods we've developed to interpret the data. Without those, the flare would have passed unnoticed. It would have been just another ripple in the universe, unrecorded and unknown. But because we have these instruments, because we're constantly observing, we were able to catch it, to measure it, to understand it, and to place it within the larger story of how magnetars behave. Out in the vast distance between stars, there is no road, no path, and no guide marking the way. And yet signals travel. They move steadily, silently, and without hesitation, crossing distances that feel almost impossible to picture. The flare from SGR 1806-2 owed it exactly that. Once the energy left the magnetar, it didn't pause or scatter randomly. It began a long journey, one that would take tens of thousands of years to complete, and all of it happened at the speed of light. That phrase is familiar, but it's worth slowing down for a moment and sitting with it. The speed of light is not just fast. It is the fastest speed anything can travel through space. Nothing with mass can exceed it, and even light itself doesn't go any faster. It moves at a constant rate, covering vast distances in what, from our perspective, feels like no time at all. But when the distances become large enough, even light takes time, a lot of time. The signal from SGR 1806-20 travelled for about 50,000 years before it reached Earth. That means the flare itself occurred 50,000 years ago, long before any modern human civilization existed. It happened while early humans were still moving across landscapes, learning, adapting, and building the first simple tools. And only in 2004 did that signal finally arrive here. There's something quietly remarkable about that. Because when we detect a signal like this, we're not observing the present state of the universe, we're observing its past. Now let's gently follow that journey. When the flare occurred, gamma rays were emitted outward in all directions. Each photon, each tiny packet of energy, began moving through space. There was no atmosphere to slow it down, no medium to resist its motion, just open space. And space, despite feeling empty, is not entirely nothing. There are particles, there are fields, there are regions of gas and dust. But compared to the density of matter on Earth, it's incredibly sparse. Which means that most of those gamma rays travelled without interruption. They didn't collide with anything, They didn't change direction, they simply continued forward. Now, as they moved, they spread out. The energy of the flare was distributed across an ever-expanding sphere. The farther the signal travelled, the larger that sphere became, and the more diluted the energy became at any single point. This is an important idea. The total energy remains the same, but it is spread over a larger area, so the intensity decreases with distance. That's why something so powerful at its source becomes subtle by the time it reaches us. Now, imagine that expanding sphere moving outward through the galaxy. At first, it passes through the immediate surroundings of the magnetar, nearby gas clouds, other stars, regions shaped by previous stellar activity. Then it continues outward, crossing spiral arms, drifting through interstellar space, moving past regions where new stars are forming and others where old stars are fading. All the while, the signal remains the same, a burst of gamma rays carrying information about the event that produced it. Now, there's another detail worth noticing. The signal doesn't arrive all at once in the sense of being perfectly uniform. Different parts of the flare have slightly different structures. The initial spike, the tail, the pulses, all of these features are preserved as the signal travels, so when it reaches Earth, we don't just detect a single flash. We detect the shape of the event, the timing, the variations. It's like receiving a message that contains not just a word, but a pattern. And by reading that pattern, we can reconstruct what happened at the source. Now, there's something interesting about how precise this process is. Even after travelling for 50,000 years, the signal retains its structure well enough for us to measure details on the scale of fractions of a second. That means the information carried by the gamma rays is remarkably stable. It doesn't degrade in a way that erases the timing of the event. It doesn't blur into something unrecognisable. It arrives with enough clarity that we can still see the pulses tied to the magnetar's rotation. And that allows us to connect the signal back to its origin. Now, if we think about this in a more familiar way, it's a bit like hearing a distant echo. But instead of sound travelling through air, it's light travelling through space. And instead of arriving seconds later, it arrives tens of thousands of years later. Yet the principle is similar. A signal leaves its source, it travels, and eventually it reaches an observer. Now, there's also something else happening during this journey, though it's very subtle. The expansion of the universe can affect the wavelengths of light, travelling over extremely large distances, stretching them slightly. But for something within our galaxy, like SGR 1806-20, this effect is minimal. The signal arrives largely unchanged in terms of its energy and timing, which makes it easier to interpret. Now, as the signal approaches Earth, it encounters something new, the Earth's environment. First, it meets the outermost regions of our planet's influence, the magnetosphere. This is the region dominated by Earth's magnetic field, which deflects many charged particles from space. Gamma rays, being neutral, are not deflected in the same way, but they pass through this region and continue toward the atmosphere. Then they reach the ionosphere. This is where the interaction becomes noticeable. The gamma rays deposit energy into the upper atmosphere, increasing ionization and causing the subtle effects we discussed earlier. Changes in radio propagation, small disturbances in the structure of the ionosphere, and then, for the most part, the signal is absorbed. The atmosphere prevents the gamma rays from reaching the surface in significant amounts, which is why we rely on satellites to detect them. Now, if we step back and look at the entire journey, there's a sense of continuity. An event occurs. Energy is released. That energy travels across space. It reaches us, and we detect it. It's a chain of events that connect something happening far away and long ago to something we can observe here and now. And that connection is what makes astronomy so unique. We don't travel to these objects, we don't interact with them directly, but we receive their signals, and those signals carry stories. Now there's a quiet implication in all of this. Every time we look at the sky, we are looking into the past, not just in a general sense, but in a very specific, measurable way. Light from the moon takes about a second to reach us. Light from the sun takes about 8 minutes. Light from distant stars can take years, centuries, or much longer. And in this case, the signal from SGR 1806-2 took 50,000 years. So what we observed in 2004 was not happening at that moment. It had already happened, long ago, and we were just receiving the message. Now this idea can feel a bit abstract, but it becomes more tangible when you think about it in terms of sequence. The magnetar flared, the gamma rays were emitted, they began their journey, they crossed the galaxy, and eventually they reached Earth. Each step follows the previous one, each part of the story is connected, and we, as observers, are simply at the end of that chain. Now, as we continue, there's another aspect worth exploring, because while we've been focusing on how the signal travels, we haven't yet considered how different forms of energy behave once they leave the source. Why gamma rays are so effective at carrying this information, why they can travel such distances, and how they differ from other forms of radiation. Picture, for a moment, the idea of an explosion as we usually understand it. There's a sudden release of energy, a sharp sound, a wave of pressure that moves outward, pushing air, rattling windows, maybe even shaking the ground beneath your feet. It's loud, immediate, and unmistakable. Even if you close your eyes, you can still feel it and hear it. That's how explosions work here. But space is different. There is no air, no medium to carry sound, no pressure wave moving outward in the way we're used to. And yet, events like the flare from SGR 1806-20 are still described as explosions, which might seem a little confusing at first, because if there's no sound, no blast wave, no roaring impact, what exactly makes it an explosion? The answer lies in what's actually being released, not air pushed outward, not a shockwave travelling through a dense medium, but energy, pure energy, moving outward as radiation. When the magnetar's crust cracked and its magnetic field reconfigured, the energy didn't push against anything nearby in the way an explosion on Earth would. Instead, it was converted into high-energy photons, primarily gamma rays, and those photons streamed outward in all directions. So instead of a boom, you get a flash. Instead of a shockwave, you get a burst of light. And that light carries the energy across space. Now, if we pause here for a second, there's something quietly interesting about that, because it means that the most powerful explosions in the universe are often completely silent. Not quiet in the sense of being gentle, but silent in the sense that there is nothing to carry the sound. If you were somehow close enough to witness such an event, and if we set aside all the reasons that wouldn't be possible, you wouldn't hear anything at all. You would only see, or more accurately, you would detect radiation, gamma rays, X-rays, and other forms of light. Now, this changes how we think about intensity. On Earth, intensity is often tied to sound and force. A louder explosion feels more powerful, a stronger shockwave feels more destructive. In space, intensity is tied to energy carried by light. How much radiation is emitted, how concentrated that radiation is, and how quickly it's released. The flare from SGR 1806-20 was intense not because it shook space, but because it released an enormous amount of energy in a very short time. That energy travelled outward as gamma rays, and those gamma rays carried all the information about the event. Now, there's another layer to this. Even though there's no sound in space, the processes happening during the flare are still dynamic. Magnetic fields snapping into new configurations, particles being accelerated, energy being converted from one form to another. If there were a medium to carry those motions as sound, it would likely be an incredibly complex and powerful signal. But in the absence of such a medium, all of that activity is translated into radiation. Light becomes the messenger. Now, it's also worth noting that not all of the energy from the flare leaves as gamma rays. Some of it remains near the magnetar, trapped temporarily in the form of a hot plasma, a kind of fireball made of charged particles and radiation. This plasma is held in place by the magnetic field, at least for a while. As it evolves, it emits radiation, contributing to the tail of the flare that we detect. So even after the initial spike, there's a continuing process of energy release, shaped by the magnetic field and the rotation of the star. But again, all of this happens without sound, without pressure waves, without anything we could hear. Now, if we shift perspective slightly, there's something almost calming about that. The idea that even the most energetic events in the universe unfold in silence. No sudden noise, no overwhelming roar, just a brief flash of energy, travelling outward, carrying information across space. And that silence doesn't mean nothing is happening. It just means that what's happening is expressed in a different way. Now, bringing this back to how we detect such events, it becomes clear why radiation is so important. Because without sound, without direct physical interaction, the only way we can observe these explosions is by capturing the light they emit. Gamma rays, X-rays, and other forms of electromagnetic radiation become our primary tools. They allow us to see events that we cannot hear or feel, and in doing so, they reveal a universe that behaves quite differently from our everyday experience. Now, there's also an interesting contrast between the quietness of space and the intensity of what's happening within objects like magnetars. Inside the star, the conditions are anything but calm. The magnetic field is under tension. The crust is under stress. Particles are being accelerated to high energies. Energy is being stored and released. It's an environment of constant activity. But once that energy leaves the star, it moves into a medium where it can only travel as radiation. And that transition from internal activity to external silence is part of what makes these events feel so different from anything we experience directly. Now, if we think about this in terms of perception, it highlights something about how our senses shape our understanding. We're used to associating events with sound and motion. We expect explosions to be loud. We expect powerful events to be felt physically. But in space, those expectations don't apply. Instead, we rely on instruments. Detectors that can capture radiation. Systems that can measure energy. And through those tools, we build a picture of what's happening. Now, there's one more aspect worth considering. Even though space is silent, the information carried by radiation can be incredibly rich. The energy of the photons tells us about the processes that produced them. The timing of their arrival reveals the structure of the event. The patterns in the signal, like the pulse tail of the magnetar flare, provide clues about the rotation and behaviour of the source. So while we don't hear the explosion, we can still understand it in great detail. In some ways, more detail than we might get from sound alone. Now, if we step back and look at the broader picture, there's a kind of quiet consistency here. Energy is released. It travels outward as light. It crosses space. It reaches us, and we detect it, all without a single sound. It's a different way of experiencing the universe, one that relies on observation rather than sensation, measurement rather than perception, and yet it allows us to connect with events happening across vast distances. Every time you look up at the night sky, you're not seeing things as they are. You're seeing them as they were. It's a simple idea, but one that becomes more meaningful the farther you go. Light takes time to travel, and even though it moves as fast as anything can, the distances in space are so large that delays become unavoidable. What we receive is always a record of the past, carried to us by light that has been on its way for a very long time. In the case of SGR 1806-20, that delay is about 50,000 years, which means that the flare we detected in 2004 did not happen in 2004. It happened 50,000 years earlier, and what we observed was the arrival of that event, not its occurrence. Now, it helps to slow that down because it can feel a little abstract. Imagine sending a message across a very large distance. But instead of taking seconds or minutes to arrive, it takes tens of thousands of years. By the time it reaches its destination, everything at the source has already moved on. The moment that created the message is long gone. That's what light does in the universe. It carries information across space, but it also carries delay. And that delay is what allows us to see the past. Now, this isn't unique to Magnetars or distant explosions. It applies to everything we observe in the sky. The moon, for example, is about 1 light second away. So when you look at it, you're seeing it as it was 1 second ago. The sun is about 8 light minutes away. So sunlight takes 8 minutes to reach Earth. If the sun were to suddenly change, we wouldn't know about it for 8 minutes. Stars in our galaxy can be dozens, hundreds, or thousands of light years away, which means we see them as they were decades, centuries, or millennia ago. And objects like SGR 1806-20, located tens of thousands of light years away, show us events that happened long before recorded history. Now, there's something quietly consistent about this. Distance and time are linked. The farther away something is, the further back in time we're looking. So when we observe the universe, we're not seeing a single moment. We're seeing many different moments at once. Each object, each signal, arrives with its own delay, and together they form a layered view of the past. Now, if we bring this back to the flare, it becomes easier to understand what we actually detected. The magnetar released its energy. The gamma rays began their journey, and for 50,000 years they travelled through space, passing through regions of the galaxy, moving steadily outward, unaffected by time in the way we experience it, until finally they reached Earth. And in that moment our instruments recorded something that had already happened long ago. Now, there's an interesting implication here. When we observe an event like this, we are not just learning about the object, we are learning about its history. The flare tells us what the Magnetars was doing 50,000 years ago, but it doesn't tell us what it's doing now. For all we know, the magnetar could have changed since then. It could have produced more flares, it could be quieter, it could be in a slightly different state. But we won't know until the light from those later events reaches us. So in a sense, astronomy's always a bit behind. We're constantly catching up with the universe, receiving signals that were sent long ago and using them to build a picture of what's happening. Now, that might sound like a limitation, but it's also a powerful advantage, because it allows us to study processes over time. When we look at distant objects, we're seeing earlier stages of the universe. When we look at closer objects, we're seeing more recent ones, and by comparing them, we can piece together how things change. Now, in the case of SGR 1806-20, the flare is a single event, a moment, but it fits into a larger timeline. The magnetar formed long before the flare. It evolved. It built up magnetic stress. It released that stress in 2004, from our perspective, but in reality, 50,000 years ago. And it has continued evolving since then. We just haven't seen those later stages yet. Now, there's something else worth considering. Time doesn't flow differently for the light itself. From the perspective of a photon, the journey from the magnetar to Earth is instantaneous. It doesn't experience time in the way we do, but from our perspective, that journey takes 50,000 years, which means that time, as we experience it, is tied to our frame of reference. We measure it based on how long things take to reach us. And in astronomy, that measurement becomes a way of looking into the past. Now, if we step back and think about this more broadly, it changes how we think about observation. We're not just seeing objects, we're seeing events at different points in time. The sky is not a snapshot of the present, it's a collection of moments, each arriving at its own pace. And that's true for everything. The light from a distant galaxy might have started its journey billions of years ago. The light from a nearby star might have left a few years ago. And the light from the magnetar flare left 50,000 years ago. All of it arriving here, now. Now there's a quiet continuity in that idea. The universe is constantly sending out signals, light, radiation, information, and those signals are constantly arriving. We're always receiving something, always detecting events that have already happened. Now, bringing this back to the flare, it highlights something important about how we interpret what we see. The event itself is over. It's not happening now. But the information it carries is still valuable. It tells us about the conditions inside the magnetar, about how magnetic fields behave, about how energy is stored and released, and even though the event is in the past, the knowledge we gain from it is very much in the present, because while time and distance shape how we receive signals, they also shape how we compare events, how we place them within the larger context of the universe. Across the galaxy, SGR 1806-20 is not alone. It might stand out because of what it did in 2004, but it belongs to a small group of objects that share similar characteristics. They are scattered through the Milky Way, often hidden in dense regions filled with gas and dust, and for the most part they remain quiet. Not silent in an absolute sense, but quiet enough that you wouldn't notice them unless you were specifically looking for their signals. These are magnetars, and while each one has its own behaviour, they all follow the same general pattern. They rotate, they emit radiation, they occasionally produce bursts, and every so often, one of them releases something much larger. Now it helps to take a moment to consider just how rare they are. The Milky Way contains hundreds of billions of stars. Out of all of those, only a small fraction have ended their lives as neutron stars. And out of those neutron stars, only a small fraction are magnetars. So when we talk about magnetars, we're already dealing with a very select group of objects. Not common, not widespread, but not entirely unique either. Now, among the known magnetars, there are a few that have been studied in detail. Objects like SGR 1900, +14 and SGR 0526-66 have also produced giant flares, though not as powerful as the one from SGR 1806-20. These events, observed in different years, provide additional data points. They show that giant flares are not a one-time occurrence tied to a single object. They are part of a broader behaviour associated with magnetars, but they are rare, very rare. Most of the time, magnetars behave in a much more subdued way. They emit smaller bursts of gamma rays and X-rays, short flashes, brief signals, sometimes occurring in clusters, sometimes separated by long periods of inactivity. These smaller bursts are thought to be caused by minor adjustments in the star's magnetic field, small releases of stress, tiny shifts compared to the large-scale reconfigurations that produce giant flares. Now, there's something interesting about this contrast. The same object that can produce one of the most powerful explosions ever detected can spend long periods doing very little. It doesn't constantly release energy at that level, it builds, it stores, and then occasionally it releases. That pattern shows up in many natural systems. Long periods of stability, followed by sudden change. Now, if we look at magnetars as a group, there's a range of behaviours. Some are more active, producing frequent bursts. Others are quieter, with long gaps between events. Some show strong X-ray emissions, others are more subtle, but they all share the same underlying mechanism, a powerful magnetic field, a dense, compact structure, and the ability to store and release energy through changes in that field. Now, one question that often comes up is whether SGR 1806-20 is unique. The answer is both yes and no. It's not unique in the sense that it's the only magnetar capable of producing a giant flare. Other magnetars have done so, but it is unique in terms of the scale of the flare we observed. The 2004 event remains the most powerful giant flare ever recorded, so while the mechanism is shared, the magnitude of that particular event stands out. Now, there's another layer to this. Some events that we classify as short gamma ray bursts, especially those detected in distant galaxies, may actually be giant flares from magnetars like these. The difference is distance. When a giant flare occurs in another galaxy, far beyond the Milky Way, its signal is weaker by the time it reaches us. We might not detect the pulse tail, we might only see the initial spike, and without the additional information, it can be difficult to distinguish between different types of events. So by studying nearby magnetars, like SGR 1806-20, we gain a reference point, a way to recognise similar events at greater distances. Now, if we step back and look at the broader picture, magnetars occupy an interesting place in the universe. They are not as large as stars in their main phase of life. They are not as massive as black holes. But they represent a state of matter and energy that is pushed to its limits. They are compact, dense, magnetically intense, and capable of producing events that briefly rival much larger systems. Now there's something quietly balanced about how they exist. Most of the time they are stable, rotating slowly, emitting radiation, existing as what might be called quiet giants. Not giant in size, but in potential, because the energy stored within them is enormous, and that energy doesn't disappear. It remains, waiting, building. Now, over long periods, magnetars can evolve. Their magnetic fields may decay. Their activity levels may change. They may become less active, producing fewer bursts, or they may enter periods of increased activity. The details of this evolution are still being studied. But what's clear is that magnetars are not static. They change over time, and those changes can lead to different kinds of behaviour. Now, bringing this back to SGR 1806-20, it becomes easier to place it within this group. It's not an isolated phenomenon. It's part of a class of objects that share similar properties, but it also represents an extreme example within that class, a case where the conditions aligned to produce a particularly powerful event. Now, there's something useful about having both the general and the specific. The general tells us how magnetars behave overall. The specific tells us what they're capable of under certain conditions, and together they give us a more complete understanding. Now, as we continue, there's one more question that naturally arises. If magnetars are capable of producing such powerful flares, and if they exist in our galaxy, how often do these events actually happen? Every now and then, after learning about an event like the 2004 flare, a quiet question tends to linger. Not in a dramatic way, not with urgency, but simply as a natural extension of curiosity. Could it happen again? And the answer, when approached calmly, is yes. But the way that yes fits into the larger picture matters much more than the word itself. Because events like the giant flare from SGR 1806-2 are not one-time impossibilities. They are part of how magnetars behave. We know this not just from a single observation, but from multiple objects showing similar, though usually smaller, activity over time. Magnetars build up energy. They store it in their magnetic fields. They release it in bursts, sometimes small, very rarely very large. So in that sense, the process is ongoing. The magnetar that produced the 2004 flare still exists. It continues to rotate. It continues to emit radiation. And over time, its magnetic field continues to evolve, which means that eventually it could produce another flare. But here's where the scale of time becomes important. These giant flares are rare, not just uncommon, but separated by long intervals. Based on what we have observed so far, a magnetar might produce a giant flare only once, every few hundred to a few thousand years. That's not a precise number, but it gives a sense of spacing, long gaps, long periods of quiet, followed by a brief moment of activity. So while it can happen again, it doesn't happen often. Now, if we widen the view beyond a single magnetar, the picture changes slightly. There are multiple magnetars in the Milky Way. Not many, but enough that, over long periods, the chance of one of them producing a giant flare becomes more likely. If each magnetar produces a giant flare only rarely, but there are several magnetars, then across the entire galaxy, these events may occur occasionally. Still not frequent on a human timescale, but not entirely unique either. Now, there's another factor to consider: distance. Even if a giant flare occurs somewhere in the galaxy, whether we detect it clearly depends on how far away it is. The closer the event, the stronger the signal we receive. The farther away, the more diluted it becomes. So some flares may happen without us noticing them in detail, simply because they occur too far away to stand out, which means that what we observe is only part of the full picture. Now, bringing this back to SGR 1806-2O specifically, it's still an active object. It continues to produce smaller bursts from time to time. These are part of its normal behaviour. They don't release nearly as much energy as a giant flare, but they show that the magnetar is still evolving, still adjusting, still storing and releasing energy in smaller amounts. And that ongoing activity suggests that the underlying processes are still at work. Magnetic fields shifting, stress building, energy accumulating. Now, whether those processes will lead to another giant flare in the near future is uncertain. Not because it's impossible, but because the timing is unpredictable. We don't have a way to look inside the magnetar and measure exactly how much stress has built up or how close it is to another large release. We can observe its emissions, we can track its behaviour, but the exact moment of a giant flare is not something we can predict with precision. It's more like a threshold, a point at which the system can no longer maintain its current state, and when that point is reached, the release happens. Now, there's something quietly reassuring about how this fits into the larger structure of the galaxy. Even though magnetars are powerful, and even though their flares can be intense, the distances involved are vast. The chances of one occurring very close to Earth are low, and as we discussed earlier, distance plays a key role in reducing the impact of these events. So while it's interesting to ask whether it could happen again, it's also important to place that question in context. Yes, it can. Yes, it likely will, somewhere in the galaxy. But no, it's not something that happens frequently in our immediate surroundings. Now, there's another angle to this question that's worth considering, not just whether it will happen again, but whether we will be ready to observe it when it does. In 2004, we had satellites in place, instruments ready, systems capable of detecting and recording the event, and since then, those systems have improved. We have more advanced detectors, more satellites, better coordination between observations, which means that the next time a giant flare occurs, we may capture even more detail. We may learn more about the structure of the event, more about the timing, more about the energy distribution, and that's one of the interesting aspects of studying rare events. Each occurrence becomes an opportunity, chance to refine our understanding. Now, stepping back for a moment, there's a pattern that becomes clear. Magnetars are not constantly dramatic. They spend most of their time in a state of relative calm. They rotate, they emit radiation, they exist, and then occasionally they release energy in bursts. Most of those bursts are small, some are larger, and very rarely one becomes a giant flare. So when we ask whether it could happen again, we're really asking whether that cycle will continue, and the answer is that it will, over long periods, across different objects, in different parts of the galaxy. Now, there's something quietly balanced about that. The universe is not static. It's not unchanging, but it's also not chaotic in a constant, unpredictable way. It follows patterns, cycles, processes that unfold over time, and magnetars are one example of that. Far beyond anything we experience in daily life, the universe has a way of pushing its own rules to their limits, not by breaking them, but by exploring the edges of what those rules allow. And when we look at something like SGR 1806-2O, we're not just observing a single object or a single event. We're looking at a place where multiple extremes come together at once. Extreme density, extreme magnetism, extreme energy release, all contained within something no larger than a city. Now, it helps to pause for a moment and consider how unusual that combination really is. On Earth, when we think about powerful systems, we usually imagine something large. Storm systems span continents. Oceans cover vast areas. Even the sun, the most dominant object in our sky, is enormous compared to our planet. Size and power tend to go together. But magnetars challenge that idea. They show us that power doesn't always come from size. It can come from concentration, from how tightly matter is packed, from how much energy is stored in a small space, and from how quickly that energy can be released. Now, SGR 1806-20 represents one of the clearest examples of this. A remnant of a once massive star compressed into a sphere about 20 kilometers across, holding within it a magnetic field so strong that it reshapes how matter behaves, and then, for a fraction of a second, releasing a portion of that stored energy in a way that briefly makes it one of the brightest sources of radiation in the galaxy. That's not just extreme, it's a different way of thinking about what's possible. Now, there's something interesting about how these extremes arise. They don't appear randomly. They are the result of processes that follow clear physical rules. A massive star forms, it lives, it exhausts its fuel, it collapses. Under the right conditions, that collapse produces a neutron star. And under even more specific conditions, that neutron star becomes a magnetar. Each step follows from the previous one. Each stage builds on what came before. So while the final result feels unusual, the path leading to it is part of a larger, understandable process. Now, if we look at the flare itself, it also fits into that pattern. Energy is stored in the magnetic field over time. Stress builds in the crust. At some point, that stress is released. The magnetic field reconfigures. Energy is emitted as gamma rays. Again, a sequence, a process. Not random, but governed by the same physical laws that apply everywhere else. Now, what makes it feel different is the scale. The conditions are so far beyond what we can reproduce that they stretch our intuition. We're used to thinking in terms of everyday forces. Gravity that pulls objects downward, magnetism that moves small pieces of metal, energy that warms or lights. But in a magnetar, those same forces operate at levels that are difficult to imagine. Gravity compresses matter to extreme densities. Magnetism becomes the dominant force shaping the star. Energy is stored and released in vast amounts, and yet the rules themselves remain the same. They're just being applied in a different regime. Now, there's something quietly consistent about that. The universe doesn't need new rules to create extreme phenomena. It uses the same rules, just under different conditions. And that's part of what makes studying objects like magnetars so valuable. They allow us to test our understanding of physics in environments we can't recreate. If our models work there, they're likely to work elsewhere. Now, another aspect worth considering is how these extremes fit into the broader universe. Magnetars are not the largest objects. They're not the most massive. They're not the most energetic in total output. But they occupy a specific niche. They represent the upper limits of magnetic field strength. They show us what happens when matter is compressed to its limits without forming a black hole. And they demonstrate how energy can be stored and released through magnetic processes. Now, if we compare them to other extreme objects like black holes, there's an interesting contrast. Black holes represent a kind of end point, where gravity dominates completely and even light cannot escape. Magnetars, on the other hand, are still visible. They emit radiation, they interact with their surroundings, they are active in a way that black holes are not, at least not directly. So while black holes show us one kind of extreme, magnetars show us another, an extreme where matter, magnetism and energy are still interacting in observable ways. Now, bringing this back to the 2004 flare, it becomes clear why that event stands out. It wasn't just a powerful explosion, it was a demonstration of how these extreme conditions can produce something observable across the galaxy. A brief moment where the internal dynamics of a magnetar became visible to us, where stored energy was released in a way that we could detect, measure, and study. Now there's something quietly humbling about that, because it reminds us that the universe is capable of things far beyond our everyday experience, and yet, through observation and understanding, we can still make sense of them. We can take something that seems overwhelming and break it down into processes, into steps, into explanations. Now, if we step back even further, there's a broader perspective to consider. The universe is not uniform. It contains regions of calm and regions of intensity, objects that change slowly and objects that change suddenly, processes that take billions of years, and processes that happen in fractions of a second. And magnetars sit at one end of that spectrum, representing a kind of intensity that is rare but real. Somewhere in the middle of all this, after the numbers and the mechanisms and the quiet step-by-step understanding, there's a different kind of realization that begins to settle in. Not about magnetars specifically, but about reality itself. Because when you take something like the flare from SGR 1806-20 and look at it carefully, it starts to shift how familiar concepts feel. Things like matter, energy, time, and even emptiness begin to look a little less straightforward than they once did. Take matter, for example. In everyday life, it feels solid and well-defined. You can hold it, move it, shape it. It behaves predictably. But inside a magnetar, matter is pushed so far beyond normal conditions that it no longer resembles anything we interact with. Atoms are no longer intact. Structure is no longer familiar. What we call solid becomes something entirely different. And yet, it's still matter. Still governed by the same underlying rules, just expressed in a way that feels almost unrecognizable. Now consider energy. We're used to thinking of energy as something that powers movement, heat, or light. Something that flows steadily or is used gradually. But in the case of a magnetar flare, energy can be stored quietly for long periods and then released almost instantly. Not because new energy is created in that moment, but because it has been accumulating, waiting for the right conditions to be released. That idea shows up in many places, but here it's taken to an extreme, a reminder that what looks calm on the surface can hold immense potential beneath. Now, time adds another layer. The flare we observed in 2004 didn't happen in 2004. It happened 50,000 years earlier. What we detected was the arrival of that event, not its occurrence. So when we observe something in space, we're always looking into the past. Not metaphorically, but literally. Which means that the present, as we experience it, is not something we can observe directly beyond our immediate surroundings. Everything else comes with a delay. Now that might sound like a limitation, but it also provides a kind of depth, because it allows us to see different moments in the universe at once, to observe processes unfolding over time by looking at objects at different distances. In a way, the universe becomes a layered record of its own history. Now, there's also something to be said about emptiness. Space feels empty, vast, quiet, and largely devoid of matter. But events like this show that emptiness is not the same as inactivity. Energy can move through space, signals can travel across enormous distances, fields can extend and interact. So even in regions where there's very little matter, there is still structure, still activity, still connection. Now, bringing all of this together, the flare from SGR 1806-2 becomes more than just an isolated event. It becomes an example, a demonstration of how the same physical laws we experience every day can produce outcomes that feel almost unfamiliar when taken to their limits. Gravity compresses matter. Magnetism stores energy. Time connects events across distance. Light carries information. These are not different rules. They are the same rules, applied under different conditions. Now, there's something quietly reassuring about that. The universe is not unpredictable in the sense of being random or chaotic without structure. It follows patterns. It operates according to principles that can be understood, even when those principles lead to extreme outcomes. Now, another interesting aspect is how much of this we can learn without ever being physically close to the source. We don't travel to magnetars. We don't interact with them directly. And yet, by detecting the signals they emit, we can reconstruct what's happening. We can infer the structure of the star. the behaviour of its magnetic field, the sequence of events leading to a flare, all from light that has travelled across the galaxy. That's a powerful idea, because it means that observation, when combined with careful reasoning, allows us to understand things that are far beyond our immediate reach. Now, there's also a subtle shift in perspective that comes from this. We often think of ourselves as separate from the universe, observing it from the outside, but in reality, we're part of it. The same physical laws that govern magnetars govern everything around us. The same principles that shape distant stars shape the matter in our own bodies. The difference is not in the rules, it's in the conditions. Now, if we step back one more time, there's a kind of continuity in all of this. A star forms, it evolves, it collapses, it becomes a magnetar, it stores energy, it releases that energy in a flare. The flare travels across space, it reaches Earth. We detect it, we understand it. Each step follows from the previous one. Each part of the story connects to the next. And at the end of that chain, we find ourselves. Observers, yes, but also participants in the same universe. The story of SGR 1806-2 is not just about a single event. It's about how extreme conditions reveal deeper patterns, and how, even across vast distances and timescales, those patterns remain consistent. If you've followed this journey from the beginning, then by now something very distant has become a little more familiar. Not closer in space, not closer in time, but clearer. We started with a quiet introduction, a simple idea, and slowly moved outward, step by step, into something far beyond everyday experience. A magnetar, hidden deep within our galaxy, releasing more energy in a fraction of a second than our sun produces in thousands of years. And yet, here we are, sitting comfortably, listening, thinking, perhaps letting the mind wander just a little. There's something gently grounding about that contrast, because no matter how extreme the universe becomes, no matter how far away these events unfold, your immediate surroundings remain unchanged. The room you're in, the quiet sounds around you, the steady rhythm of your breathing, all of it continues just as it was before. And maybe that's a good place to settle for a moment, noticing where you are, noticing how still everything feels compared to what we've just explored. Because out there, in distant regions of the galaxy, matter is being compressed to unimaginable densities. Magnetic fields are twisting and storing energy over long periods of time, and every so often that energy is released in a sudden flash that travels across tens of thousands of light years. But here, everything is calm. Now, if you gently think back through what we've covered, there's a kind of continuity that ties it all together. A massive star living out its life, a collapse into something smaller and denser, a magnetar forming, with a magnetic field so strong that it reshapes the structure of the star itself, stress building quietly over time, a sudden release, a flare, a signal travelling across space, and finally its arrival here, detected by instruments orbiting above the Earth. Each step follows naturally from the last. Nothing appears out of nowhere. Nothing breaks the rules. It's all part of a larger pattern. And that pattern, once you see it, begins to feel less overwhelming, because even the most extreme events are still connected to processes we can understand. Now, there's something quietly comforting about that idea. The universe is vast. It contains objects and events that go far beyond what we experience in daily life. But it is not chaotic in a way that's impossible to follow. It has structure. It has consistency. It follows rules that apply everywhere, from the smallest scales to the largest. And that means that, with patience, we can make sense of it. Now, as we come back to the present moment, it might be helpful to let some of that scale gently fade into the background. Not disappear, but settle, like a distant memory. Because while it's interesting to think about magnetars and gamma ray flares, what matters right now is where you are, the quiet around you, the sense of stillness, maybe the feeling of your body relaxing just a little more as you listen. You don't need to hold on to every detail. You don't need to remember every number or every explanation. It's enough to have followed the journey, to have spent a little time exploring something vast and distant, and then returning. Now, if you notice your breathing, just for a moment, there's a steady rhythm there. In and out, nothing urgent, nothing forced, just a natural pattern. And in a way, that rhythm mirrors something we've seen in a much larger context. Energy building, energy releasing, cycles repeating over time, different in scale but similar in pattern. Now, as everything settles, you might find that your thoughts are a little slower, a little quieter, and that's perfectly fine. There's no need to rush back to anything. The universe will continue doing what it does. Magnetars will continue evolving. Signals will continue travelling across space, and you can simply rest here for a moment, knowing that all of it is happening out there, while everything here remains calm and steady. So as we gently come to the end of this exploration, there's nothing more you need to do, no conclusion to hold on to, no final point to remember, just a quiet awareness that somewhere far away an event once happened and its light reached us. And for a little while, you followed that light. Now you can let it fade into the distance again and simply rest.